Sure. Welcome back, everyone. This is the third round of Chemenigma 2021, the analysis/design. We had released the questions 9 a.m. yesterday, and the participants had to attempt one of problem 1A or 1B. Problem 2 was compulsory, and they had to attempt one of problem 3A or 3B. They must present the solutions to the above problems mandatorily as a presentation, which they have submitted by 12 noon today. No changes shall be made to the presentation after the round starts, and any attempt to make any changes shall be met with strict penalties, not excluding disqualification. We shall begin the presentation round now. I expect it to be over in 2.5 hours. So, since we are running a little bit late, by 6:30 probably. This is the first question. Shukriya, can you go ahead and brief the question?
Yeah, so this is a question on like quantifying the explosive abilities of a battery bomb. So here the participants they are asked to be assuming that they have been inducted into a top secret research services wing of the Defense Forces of India. And they're necessary, so they're the twin objective of helping India's defense forces in high terrain with a low weight energy source. So this is necessary so that the defense forces can carry a larger ammunition weight. Now, the task is to whether a high density energy source could also supplement as an energy explosive. So that is the question which the participants have to solve. And for that, certain pointers have been provided that they realize that alkali metal oxygen batteries have the highest energy density among the known sources. And their task is to design an optimization between extracting the highest energy density possible while ensuring that the battery could still be used as an explosive at the end of its life. Certain other details have been provided as has been shown in the question. I think this provides a summary of the first question. Now I'll go over to summarize the other question. So in this, spectral analysis of chloromethane was performed, and they were given the spectral data. So from the raw spectrum, they have obtained a value of the delta for chloromethane. Now, they have to estimate the CCl bond distance, number one, using the rotational spectrum. Second is from the electron diffraction spectrum, they have to find the CH and CCl bond lengths. From the data about the X-ray diffraction, that data was also provided to them. The CCl bond length has already been computed using that data. And the potential energy of the CCl bond as a function of distance has also been provided. They've been asked to compute the equilibrium bond length using this potential energy curve. And they also have to comment on the relative values of the bond lengths which are obtained from each of the experiments, and also explain if they are different, why they are different. So this is a summary of the first question. The participants have to answer one of questions 1A or 1B. Now we'll move on to question 2. So question 2 is about a chiral reagent which has been shown. It is reacting with this substrate A to produce a product. Now the HPLC chromatograms of the product and the recovered amine have been shown in the figure. Now, they have to comment on the stereoselectivity of the reaction and also come up with a stereochemical model to explain the major product, to predict the major product of the reaction. And they'll also have to quantify the selectivity factor, of course, after deriving all the necessary equations in this regard. And they'll also have to draw an approximate reaction profile of the above reaction and to determine the difference in the rate determining transition states for the two enantiomeric substrates. So this is a summary of question number 2. It's a compulsory question which all teams have to answer. Now can we move on to question 3 and above? Yeah. So in question 3, they've been provided with benzoic acid and compounds A and B. One is benzoic acid and one is a para-substituted benzoic acid. We have defined a quantity here, delta, which is the difference in the pKa of B and pKa of A. Now, various possible substituents for Y have been provided with various values of delta. and they've been used in another reaction with sodium methox. All these, this substrate, this para substituted Y along with that sort of CHBr substitution, CHRBr substitution, that has been treated with sodium methoxide and methanol, and the products have been given. The rate constant for the above reaction with no substituent has been labeled as time. The graph of log of K by K naught. K is the equilibrium constant for one particular Y, and the K naught is the rate constant, the constant with no substitute. Yes.
So K over here is the rate constant. Just
rate constant. Yeah. Sorry. Yeah. So a rate constant for one particular with any Y variations, and K constant with no substituent. Again, the graph has been plotted. So they'll have to predict the products and the mechanism of the reaction using this graph which has been provided to them. And then in another case, the R group was varied, and the graph of log of K by K naught against delta has again been plotted. So they have to justify the reason for the change in the nature of the plot. They've also been provided with another reaction, and they have to plot a rough graph of log of K by K naught against delta for this reaction. So these are the three questions, and this is a question on organometallics, which is an alternative to question 3a. Here we have an iron forming an octahedral complex with an allylic ligand. The proton and NMR spectrum have been given at two different temperatures. One is at 70 degrees Celsius and one is at minus 30 degrees Celsius. They'll have to rationalize the spectrum and postulate the mechanism behind the change in the spectrum at different temperatures. This is a very rough and quick summary of the three questions for the interest of the general audience. And now I think we can move over to the presentations. So we'll start with Team A in this round. Team A.
Hello.
Please present your screen.
Vasu. As with the previous round, I will be speaking and my teammate Aditya Sakrikar will be presenting.
Just the time duration for this presentation shall not exceed 15 minutes. And we shall appreciate it if you keep it below that.
Okay. So the first problem we are going to discuss is the question number 2, which was basically the acylation of these compounds. Next slide, please. So the first, the main premise of this question centers around the fact that the amine given, we have a racemic mixture of the amine given, and that reacts differently with the given chiral catalyst. So we drew both the conformers of the amine given, and the benzyl group was shortened as BN. You can see that when the benzyl is at the equatorial position, there is a significant so we can see that the benzyl group causes a significant steric blockage towards the nitrogen's lone pair. So as you can see, one of the main reaction sites in this compound is the lone pair of nitrogen. If we ignore the lone pairs of oxygen, so benzyl kind of blocks it and reduces the reactivity of this compound vis-a-vis all those reactions which involve the lone pair of the nitrogen. Next slide. However, here you can see when benzyl is at the axial position, the lone pair of nitrogen is exposed and it is much more reactive. So in the question it was given that one amine reacts much more than the other. So this one is the amine that will react much more than the other amine. Next slide, please. So then it was asked to present the reaction mechanism. So acylation of an amine to produce an amide is a fairly standard process, and so we have shown the reaction mechanism for that. So it is basically substitution nucleophilic addition elimination. So first the lone pair of nitrogen attacks the carbonyl group, the intermediate shown is formed, then finally some product is eliminated and our final product, which is as shown, is formed. So we can see that our final amide is also chiral and the and the confirmation of that we saw in the earlier slide itself. Next slide, please. Then it was asked to quantify the stereoselectivity. So the most clear way to go about quantifying a stereoselective reaction is calculate the enantiomeric excess. Furthermore, we had to analyze the chromatogram. So if someone refers the chromatogram given in the question paper, there is a small in the legend given behind besides the chromatogram, it is given that so in the first peak, which represents the formation of amides, the major product formed, the major stereoisomer of the amide formed occupies 91.9%. You can see the number 91.9, and the other amide occupies 7.7%. You may note that the sum of these is not 100. We have assumed that that is due to some impurities. So for this, the enantiomeric excess for the production of amides was 84.54%. For amines, we can see that the more reactive amine will react among the racemic mixture. So the concentration of the other amine with respect to this one will increase, because that will not react as much. So we will have an enantiomeric excess for the amine mixture rates also, and not unexpectedly, it comes out to be roughly similar, 84.75%. Next slide, please. What is the energy profile diagram? So the energy profile diagram, one can see the RDS and the two TSS. Also the TSS have also been labeled. So the first TS is that of nucleophilic attack, the second TS is that of elimination. The intermediate you saw in the reaction mechanism. Yeah. Next slide. So this is a small note on reaction kinetics. So since the first transition state, which is also the rate determining step as we saw earlier, is caused due to the attack of amine on the acylating agent, the rate, so it will be first order in the substrate, and overall the rate equation may be expressed like this. Next slide, please. Finally, the question was posed that the other amine will obviously, as we mentioned earlier, not react as much due to steric reasons. So we can also reformulate that proposition as that amine has a higher energy TS. So the question asked was, how can we in some way estimate the energy between the transition states? So we made an assumption. We made the assumption that the energy of the TS, the difference in energy of the TS is roughly similar to the difference in energy of, like, the graph has been translated upwards, and as for the actual energy difference, we calculated using the delta G difference minus RT ln K. And since we saw that one amide is formed 91.9%, the second amide is formed 7.7%, so the ratio of their formations is 91.9 by 7.7, that we assume to be K. So that roughly gives us energy difference of 6.2 kilojoule per moles, which is a representation of how much the benzyl group blocks attacks due to steric steric blockage. Next slide, please. So now we arrive at question 3. So in question 3, next slide, please. So in question 3, there was this question of delta. So as you can see, the more acidic a substance is, the lesser will be its pKa. So a delta greater than 0 implies that the substituted benzoic acid is less acidic than benzoic acid itself. So that means that a donating group, like amine or phenol or something like that. So here we always consider the acidity of the carboxylic group only, by the way. So delta greater than 0 indicates donating groups, delta less than 0 indicates withdrawing groups. Next. So in the first one, we were given that the R group in the question was methyl, and we were asked to explain the V-shaped curve. Sorry.
7 minutes are over.
Okay. So we propose that the reaction mechanism which took place was E2, And so in E2 there is a slight allylic character developed. So any group, does not matter withdrawing or releasing, which can cause extended resonance, will stabilize the transition state. So hence we observe the V-shaped curve, like the lowest reactivity is that of hydrogen, that is no substituent, and any other substituent causes an increase in the rate of reaction. Next. So there was a question of describing stereoisomerism also, so we can see that is not relevant here. Next. Then there was a question that a particular reaction is destabilized by withdrawing groups, and it is a straight line, unlike the V we saw earlier. So it is destabilized by withdrawing groups and stabilized by releasing groups. So we hypothesized that the R was of such nature that SN intramolecular was happening. SN dash was happening. Next slide, please. So we propose that if the R looks like this, then the methoxide ion can attack it like this. And here we see that at the benzylic position, a slight delta positive charge is developed in the transition state. And now it is clear why, if Y is electron withdrawing, it will destabilize the whole process. So hence the general trend. Next. Moreover, the R is bulky too, so we can discount any possibility of SN2 happening. Next. Then finally we had a reaction where piperidine was reacted and there was substitution nucleophilic on the aromatic ring was happening. So here is a standard example of the formation of Meisenheimer complex. Next. A Meisenheimer complex forms here too, and so obviously a withdrawing group will stabilize the Meisenheimer complex and a releasing group will destabilize it. So next. So as you can see, hydrogen is delta is equal to 0. To the left of hydrogen is delta negative. So when delta is negative, withdrawing groups, so that will stabilize our Meisenheimer complex. So the general trend of the reaction is this. There may be some points which may be up or down also. Next. So finally we arrive at the spectroscopy question, which was the first question. So next.
For the judges, this is question number 1, not question number 3.
Yeah, that was a small typo. So we were first asked to calculate. So we were given 2 Excel data sheets, and exploiting that data, we were asked to calculate carbon chlorine and carbon hydrogen bond lengths in methyl chloride. So to better visualize the data, we plotted it. So when we plotted the data for the radial distribution function here, we can clearly see that there are these peaks, and we further observed that the first peak, represents the carbon hydrogen bond length at 1.11 angstrom. The second peak represents the carbon chlorine bond length. So this is our hypothesis, and so checking out the maximas of these peaks, we get 1.11 angstrom and 1.779 angstroms to be the bond lengths which were asked for respectively using the electron diffraction method. Next. Then there was another Excel data sheet where we were given the potential energy curve as a function of the distance between the 2 atoms. So here it is clear, that's how bonds are defined when potential energy is minimized. So when potential energy is minimized, at that point we see that the internuclear distance was 1.774 angstrom. So the potential energy method gives us the answer to be 1.774 angstrom. Then there was a question of which method is better. The potential energy method, then there was the X-ray diffraction method. We did not have to calculate anything in that, or the electron diffraction method. So we propose that the potential energy method is the best because that calculates the bond length ab initio, that because a bond is basically defined as when the potential energy between those two is minimized. So that's how it is defined. On the other hand, diffraction techniques calculate the bond length indirectly based on some scattering and based on the diffraction patterns obtained. So we hypothesize that the potential energy will always be slightly more accurate than the diffraction methods. Finally, we referred sources to sources in the internet to actually see what the bond lengths were. So we obtained that was around 1.781, and as we saw, the actual bond lengths from potential energy was 774, from electron diffraction was 779, and in the question paper X-ray diffraction was 776. So we think that these errors in part are due to systematic. Some are of course due to the nature of the methods themselves, as we explained. So I think there is a slight amount of systematic error involved, along with other errors like random errors due to methods. So yeah, and we think that the magnitude of the systematic error is approximately 0.01 angstrom. So yeah, next. So all this while you haven't really gotten a chance to meet in person, so this is a very brief description of ourselves, if you will. So it was great fun participating. Thanks very much for giving us this opportunity. We wished we could have come to the IISc campus. We'll see. We'll look forward to such opportunities in the future too. Thank you.
Thanks, Team A. Now, the judges, if you want to ask any questions, so we'll open the floor for questions.
I have a couple of questions. So can you go to slide 2 and 3? Yeah, here, this one. So you have showed the two enantiomers actually of this morpholine derivative. So this is one. Can you go to the next slide? Now, here, is this the most stable form of this, most stable conformation of this?
Actually, I think there was some misunderstanding in the writing part. So the relative stability of the amines does not matter as much as their reactivity matters towards the acylating agent. So our point is that this will be more reactive towards the acylating agent.
So that is irrespective of what the acylating agent is?
For this specific acylating agent, because this involves the lone pair of the nitrogen being exposed. So yeah, for this acylating agent,
yeah, that's fine. So, but now you are telling that between these two enantiomers, so the one where the benzyl group will be in axial. So first of all, I think whether it will be in axial or there is another conformation where the benzyl group will be in equatorial, that's another first question. Second question is that would the reactivity remain the same depending on the acylating agent? I mean, the enantiomer of the acylating agent. Let's say if you are using an enantiomeric acylating agent, then how would you explain the reactivity? Did you get my question?
Yes, I got your question.
Do you know what sort of reaction is this?
Stereoselective acylation, like
that is, of course, that's a general term. Okay, yeah, let's move ahead to the next slides. Yeah, this is all right. And actually in the final product, I think one of the question was to tell you what will be the major product, that is which stereoisomer will be the major one. I think that we explained, but you did not write the structure here. That's okay.
Can you go to the previous? Yeah. So here, if we replace Bn, replace that lone pair of N by COBN. So yeah.
Yeah, I understand. I got that. Yeah. Let's go to the energetics of that one. Energy reaction profile, I think. That was the question. Should we change the slides?
Sorry, actually I got disconnected for a bit. Can you repeat what you said?
Which ones? No, can you go to the next
The
slide?
sir is asking you to move to the energetic slide.
Yeah, I think the previous thing is okay. The energy selectivity part is all right. Yeah, I think, yeah, this is what you are showing the intermediate. This is all right. Go ahead. Next. Yeah, this is also okay. Next. Yeah, how did you, you're calculating, but just by taking the product ratio of these two, of the two enantiomers, right? So what exactly this energy you are trying to calculate here?
So we basically reasoned that, one of the products is found 91.9% and the other product is found 7.7%, right? So their ratio is approximately 12. So we reasoned that one of the products is 12 times likelier to form than the other.
Okay.
So, so then we tried to translate that into the delta G term.
Right.
And because we reasoned that, and this 12 times likeliness is coming due to the difference in the TS1 energies, because that is the rate determining one.
Okay.
Of course, there will be other factors too, like the initial reactant energies are also slightly different, but this was just a estimation. So I think this is correct to the order. Not exactly maybe, but 6.2 kilojoule per mole, I think. Yeah.
Okay. So, and in the other question 3, how did you rule out the possibility of a substitution reaction?
In which subpart, sir?
Yeah, in this case, this one, this question.
So basically, we had a V-shaped curve for this one, right?
Yeah.
So now suppose the reaction would have been SN2. So SN1 is not possible in this case because the nucleophile is quite strong. So suppose the reaction had been SN2, then you see a withdrawing group. Suppose Y would be a withdrawing group, then it would increase the delta positive charge on the carbon to be attacked, the benzylic carbon, and so instead of a V-shaped curve, we would get a straight line curve with the maximum reactivity being for withdrawing groups and the minimum reactivity being for releasing groups. But we instead got a V-shaped curve which indicates that the withdrawing or releasing nature is irrelevant here. What matters is resonance is happening. So that led us to think about different mechanisms, and E2 is not improbable here because methoxide is quite a strong base also. So abstracting that hydrogen should not be a very big deal for the methoxide thing.
Okay. All right. Yeah. Okay, I'm done. Yep.
Okay, we have about 5 minutes. Any other judges?
Yeah, Anubhav. I think Shantanu has asked quite a lot in the first two parts. So in the third part, Arpan, so you are saying that the bond length that you determine using the potential energy curve, right? That's the closest. That's what you're saying, right?
Yeah, ma'am, just a second. Can you please shift the slide to that place?
Yeah.
Yes, this is the first question.
Yeah, you can go to the where you were talking about this, where you calculated that bond length, right? Using the potential, where you had that potential energy curve.
Yeah, we found out minimum.
So so now tell me, you to get this potential energy curve, how are you estimating these lengths, right, at different points? How are you getting this potential energy curve? You were given an Excel file, right, with different distances, and then you plotted it, correct?
Right.
So how do you get those distances in reality? Like, how will you get them?
So I know of a theoretical method from my textbook.
Okay, fine. So, okay, that is fine. Yeah, you know a theoretical method. Now, you were saying that, the experimental methods like the XRD or the diffraction methods that you're using, they will have some error. But that same thing is true for your theoretical methods also, right? There will be so many error possible, right? You cannot even solve the Schrodinger equation, isn't it?
Right.
So then can you justify why this potential energy method is giving you the closest one? I mean, of course, you have your answer, which is closely matching, but then do you have a justification as to how this is happening? That was absent, I think.
So I think that this potential, so I know a theoretical way of generating this potential energy curve, but when the data for the potential energy curve was given to us, I assumed that it was generated practically in some manner. How, that I don't know. So no, if you can generate a potential energy curve practically, then that is the closest one, because I think that is directly from the definition of a bond length, and the other methods calculate it indirectly.
No, directly also, how are you calculating? That's what I'm asking, right? You have to use some approach, right? Theoretical approach, even if you're using that, there also you have errors, right? So my question is, how do you justify this? One is you're getting the result, but then the second question is your reasoning. Did you get the question? You're matching it with, you said that the error is 0.007 angstrom, right? So the question is, that's fine, you're matching it with that, but the reasoning, what is the reasoning that you're getting the closest match using this potential energy method?
I think that in the diffraction methods, we shoot a beam of electrons or X-ray photons to determine our bond lengths, bond angles, stuff like that, right? So I think that not very much, but it leaves some impact on the actual distance itself. Suppose some photon collides and bond length is temporarily shortened. I think the probe for measurement in diffraction is much more energetic than the probe for measurement in potential energy method, because probe for measurement is cause of Heisenberg uncertainty principle. So I think the probe is much less intrusive here.
See, even for your potential energy curve, you're using several approximations. Okay, anyway, think about it, okay? So just one last question I have on your reaction profile diagram that you had shown, right?
In the...
where you shown the rate determining transition state and the intermediate.
Yeah,
okay. So just tell me quickly, you have your ground state and you have your transition state, right, over here?
Yeah.
So now you have your enantiomers, correct?
Correct.
You have your starting enantiomers and you have the chiral region. So just tell me the energy difference, how would it look in the ground state and how would it look in the transition state? You got the question?
Yeah, so there would be a slight difference, as I said, in the ground state also, because the two enantiomers will not have the exact same energy, but the energy difference will be much more pronounced in the TS1, as you can see.
One second. Enantiomers wouldn't have the same energy?
Oh, no, sorry. But the TS1, in the TS1, there would be a difference.
Okay, thanks, Arpan. I'm done, Anubhav. Yeah, thanks.
So we are already past, over time, but if any professor wants to ask a quick question, you can go ahead. Okay, I just wanted to ask a very small thing. So in the question you were asked to compare the relative differences between the methods. Have you done that? You said that they're all approximately about something. So you have not compared that, right? So how can you say that there is a systematic difference between the methods?
So we actually referred the actual value from Wikipedia.
Okay, I think you have not understood the question then. You had asked to determine whether each experiment is systematically giving a different bond length, as in X-ray is giving a different bond length, electron diffraction is giving a different bond length, rotational spectra is giving. Okay, you have not done the rotational spectra calculation, right?
Yeah.
Okay, so all of those methods are giving different bond lengths. You were asked to comment on that, and not that they are giving different bond lengths from the true one systematically. That actually, all of them are giving different ones.
Actually, we had our theories about that, but nothing concrete. So we didn't write that because, but we.
Okay. Oh, but that was the question.
So basically, we we developed some models to show that electron diffraction would always give slightly more than what
Where
is.
is the model?
We have not presented that.
Okay. Okay. Thank you, Arpan. I think we are done with this presentation. We can move on to Team B. Ritik Haldar and Ankur Nath. Aditya. Yes, Aditya, you can unshare your screen. Thank you.
You can see my screen, right?
Yes.
Yes. Yes. Am I audible?
Yes.
Hello. Am I audible? I'm starting. You are starting. I'm just checking. Okay, start. So the first question is about the CCl bond length determination. So the first part was about analyzing the rotation spectrum. Here we have just defined the theory. This wasn't, I think, very necessary, but just in order to understand what delta and epsilon are in those cases, we have just derived the theory using a rigid rotor model, and the C3Cl is Prolet spheroid. So using this model, we have calculated the energy eigenvalues. These are the standard results. And the calculation has been done here. This is just simple algebra, just putting the values in here. And the length of the CCl bond calculated by rotational spectroscopy was 1.7814 angstroms. From the electron diffraction spectrum, we got these three peaks, and this peak was attributed to CH, and this peak was attributed to CCl. So the CH bond length was taken from the first maximum position, which is 1.11 angstrom, and the CCl bond length, which is the second maximum position, is 1.779 angstroms. This bond length is from electron diffraction. Next is from the potential energy. So the potential energy can be computed computationally using quantum. It has to be done properly. I would like to discuss what properly means with the judges, but I don't have time to discuss that here. So equilibrium CCl bond length would be the point of minimum potential energy, which is 1.774 angstroms as calculated from our program. And so we need to compare these bond lengths, and from what we have seen, these are truly systematic differences. And these are not just random errors, these are attributed to the experiment itself. So let's start. From the potential energy calculation, I believe, like, the exact things were not given in the question, but I believe that this was done assuming the nuclei to be at rest and using the Oppenheimer approximation. So the equilibrium position would be at the potential minimum with the nuclei at rest. And in that case, the bond length is minimum. In the rotational spectrum, what we have is centrifugal distortion. The potential, it's not a rigid rotor model as we had used previously. This potential energy, it's not some kind of a step function or something like that. It's not a very steep function. There is a finite minimum here. So in that case, there would be spring constants involved, and that would result in centrifugal distortion. So it can be shown that the correction term for the non-rigid rotor model, which involves spring constants, is -4t j plus 1 cube. So there is an overestimation of bond length even when this j or the angular momentum magnitude is equal to 0. So in that case, since there is this negative difference, so we would overestimate the bond length, and that is what happened exactly. The bond length was the largest. In electronic diffraction, electrons do not directly cause rotational transitions, but from what I have read in one of our references, it was said that they interact strongly with the electron cloud and they can undergo multiple scattering. So in that case, I would believe that there could be some sort of thermal relaxation effects which could provide some amount of energy, like some sort of a temporary heat bath to the bond stretching and rotation, which would give us greater experimental bond lengths. Also in X-ray diffraction, it was written in the same reference that X-rays do not interact too strongly with the electron cloud. The small difference in bond length, which was there with respect to the potential energy calculation, was 0.002 angstroms. And I believe that even this is systematic because there are inherent nuclear velocities at non-zero temperatures. Also, these are quantum mechanical systems. So 0-point energies would come into the picture, which like in these cases, these potentials aren't harmonic. So in a harmonic potential, the deviation, the average value of the deviation from its minimum is 0. But in an anharmonic potential, that deviation, the expectation value of the deviation from the potential minimum is not 0. And since these are all experimental values, what we get are expectation values, not true minima. In that case, I think that is what causes this deviation from the equilibrium bond distance as calculated from the bond length minimum. And now we are comparing our methane versus deuterated methane. So again, I had mentioned centrifugal distortion. So I've just done the calculation here. So what happens in this case, this is just a reference picture, is that if we assume this to be the reduced mass for the CH system, then there is, since rotation is occurring, there is a centrifugal force if I'm in the frame of the rotating molecule, rotating moiety, and there would be a spring constant here because of the well nature of this potential curve. So in the classical picture, the true equilibrium in this this model with motion, like this non-static picture, would be an equilibrium, mechanical equilibrium in this way. So the equilibrium in this picture would be the equilibrium at rest divided by some factor. Now, looking at this factor, we see there is a term L square here. So L square, that is quantum mechanically, that's quantum mechanically determined and it's quantized. So we would need to look at mu. Now, mu of CH is less than mu of carbon deuterium bond. Hence, the radius of the CT bond is closer to the equilibrium radius calculated from potential energies. That's my part. Ritik is presenting question 2.
So my question is kinetic resolution question. In the question it was asked what is the selectivity of the reaction. The selectivity of the reaction is enantioselective. Here the acylation of the racemic mixture of morpholine derivative using the chiral reagent gives only one of the enantiomer of the product in excess. So our hypothesis is only the S enantiomer of the reactant can interact with the chiral reagent, and thus S enantiomer of the product forms in the excess. You can see in the right side of the, you can see the initial S reactant and initial the product S. So next slide, Ankon. So you are going to use the Felkin-Ahn model to explain the observed yield. Here there are two enantiomer of the reactant present, R and S. The nucleophilic, this is the nucleophilic addition reaction. You can see in the right side the N of the nucleophile, N nucleophile from the one of the reactant is attacking of the chiral reagent in the acyl group. Carbonyl of the acyl group. So there are many possibilities of approaching the nucleophile maintaining the Bourget-Dunich angle, but the Felkin-Ahn model says that nucleophile comes from the less hinder side. Next slide. So we are assuming here the reactant is in the reactant is in the chair form, and it is the most stable conformer, and to stabilize the transition state, where we have seen that the H bonding between NH group of the reactant and the amino carbonyl of the chiral reagent further restricts the possible conformation for the reaction. Still, there are two possible conformation which the reactant can form hydrogen bonding reagent, N in the equatorial position and N in the axial position. You can see in the right side, the above one is the N is the axial position, and you can see a significant steric hindrance. Though we have not substituted the R group here, but we have to exclude the N in the axial position. So next slide, Ankul. So we can draw all the possible conformation for the nucleophilic attack for the reaction restricted by Felkin-Ahn model and Bourget-Dunich angle. From there we can analyze which reaction is faster comparing the transition state. You can see the possible geometries for S enantiomer. S enantiomer, you can see the benzyl can live in the axial position, and the equatorial position, the two conformations of S, and they are reacting. And we have drawn the reactant, the reagent in the gray because it is below this reactant in the black. So next slide. Similarly, this is the possible geometries for reaction in the R enantiomer. You can see both of the enantiomer, one in the axial position, one in the equatorial position. Next slide, Ankon. So from there we can see what are the transition state. They are actually not the transition state. They are actually the intermediate. From the Carter-Hammett principle, we can say that the transition state is very close to the intermediate. So you can see the transition state of the S enantiomer here. For the equatorial, there is no significant steric hindrance, but for the axial one, there is significant steric hindrance. So this conformation is not possible. Next slide, Ankon. For the R enantiomer, you can see for the both of the isomers, you can see there is a significant steric hindrance. So it is also not possible. Next slide. The equatorial S has the most stable transition state. You have seen previously the nucleophilic addition rate is the rate determining state. So reaction from the S is kinetically more favorable compared to the other conformation. And this is the reaction. You can see this group is falling apart, and it is the major product. Next slide. We can calculate the selectivity from here. For the R isomer, AR is the initial R reactant, X is the chiral reagent, K slow is the rate determining step. Rate of the rate determining step. AR is equal to it at any time, concentration of AR. AR0 is equal to at any time, concentration of AR at any time, at the initial. It is A, initial it is A, at the any time it is A minus X, and initial concentration of X0 is equal to X0. Similarly for S isomer, you can see the rate equation dx dt is equal to K slow and dy dt. Similarly, from there we can get dy dx using the proper limit 0 to y, 0 to x. We can get this reaction at the t is equal to n, AR is equal to AR concentration of AR is equal to A minus X, concentration of AS is equal to A minus Y, or concentration of BR is equal to X. Since the x plus y is equal at the end of the reaction, x plus A was equal to y because the consumption is 50%. Next slide. From the equation we can get the selectivity S is equal to K fast by K slow is equal to the given ln of the reaction. From the chromatogram data, next slide, in the chromatogram data you can see the area is proportional to the concentration. Previous slide.
12 minutes.
Previous slide, please. From there we can calculate the AR by AS, which is equal to A minus X by X, and BS by BS, X by. You can see there is a 1.5% difference between them, which is coming from the systematic error from the integral calculation, and we can take the average is 12.026. Next slide. From there we can calculate the selectivity in putting in the equation, and it is coming 32.136, and this is the rate determining. This is the next slide. This is the reaction profile. You can previous slide. You can see the first step is the rate determining step because two large group is coming closer. Due to second, the reaction is endothermic because of the product has more enthalpy. Next slide. Next slide. You can calculate the delta of delta G from here, which is equal from the RNA equation. We can get the e to the power whatever it is. Then delta of delta G is equal to RT lns, and it is 8.597. Ankon, it is next yours.
Yes, so this is the question 3, the iron focus question.
This one you have about 2
Yes,
minutes.
I'll just finish in 2 minutes. So our hypothesis is that this is the equilibrium structure that we have, and this equilibrium structure, in this structure, the allylic ligand can undergo reorientation through this eta1 intermediate. And from the NMR spectra, if we consider our hypothesis, that's exactly matching with what we see from the spectra. At minus 30 degrees centigrade, we have this kind of structure. So in this case, we can see that these two protons are not equivalent, and these two protons are equivalent. These two protons are equivalent. In that case, this triplet of triplets would, these two triplet of triplet and doublets would be explained. At 70 degrees centigrade, this spectrum can only be explained if we consider these two protons to be equivalent. And why that is happening is given in the next slide. So this is because the allylic ligand in the eta3 state undergoes reorientation through an eta1 intermediate state, which has been shown here. So there can be CC rotations about this bond and CM rotations about the single bond. At lower temperatures, the rate constant of this exchange is lower than the coupling constant J. However, at higher temperatures, this rate constant becomes greater than J, resulting in a self-decoupling mechanism that causes the H2 and H1 protons to become essentially equivalent. But what this means is that since in NMR we sample from finite points of data, the protons H1 and H2 become magnetically equivalent at the time scale of this NMR reaction. That's it. Thank you.
So your differences.
Did I stop presenting? We had a few references. Sorry, I stopped presenting.
Wait, you still have some seconds left.
We have completed our presentation.
Okay, these are the references.
Yeah, could you please share the screen? Yeah, so that the judges can ask questions. It'll be easier.
Isn't my screen shared?
Yeah, it's visible.
Yes, yes.
Okay, thank you.
Sir Mukherjee, were you saying something?
No, I was asking them to share the slide. I have some question, but I would wait for if anybody else has any question, then I'll go.
Other judges, do you have any questions?
If not, then I have.
Okay, sir, I think you can start.
Okay, yeah, can you first part? I think the question number 2, I guess.
Yes, sir.
Yeah. Yes, sir.
Yeah, I think you go to the slide where you have compared the two enantiomers.
Oh, okay, sir. Sir, do you mean the reactants or the transition state?
The intermediate, whatever you had.
Okay, intermediate, yes, sir.
This is for the S enantiomer.
No, you go to the one. Okay, yeah, I think it's fine. You have separately in 2 different slides. So you think if you want to get the other product enantiomer, what would you change?
What do you mean? What, sir? I did not understand the question.
In this reaction, you are saying that the S amide will be formed, right?
Yes.
And R amine will be unreacted.
Okay.
Isn't it? That's what you were saying.
Yes.
Now, if I want to get the R amide, what would you change? What would you do? Instead of S amide, if I want to get the R amide in this reaction.
Ankon, can you go to the slide?
Which slide?
The next slide. Next slide. Yes. For R, we can for R. So we can change.
Yeah, tell me.
What you are saying?
Did you mean that we want the R enantiomer purely, or would we be fine with just mixture?
No, purely means it will not be 100% R enantiomer, but predominantly R, let's say.
Okay.
So, can we change the reagent?
What would you like to change in the reagent?
I can change the pH group to a small group, CH3 like.
Would that make a difference?
There will be not significant static hindrance.
Now, okay, go to the next slide. I think maybe you are not getting my question. Go to the next slide once. Slide 17. Yeah. So in this case, the major product is the S product. Okay.
Yes.
That's the predominant one, right? Now I want R product as the predominant one. So what would you change? In the accelerating agent?
The chirality of the reagent.
So what exactly do you mean? You are going in the right direction.
If we change the chirality of the reagent, I think it will change the static hindrance of the what you have mentioned earlier. It will only react with the R enantiomer. So I think we will get the.
Okay, so by changing the chirality of the reagent means, would you make it from cis to trans, or what would you do?
I think if this group behind the pH CH2 pH come and interact with the CH2 pH, so it will not the S enantiomer will not react with the reagent.
Okay.
So.
Okay. Yeah, I think I go to the next slide where you have done the calculations.
Yes, sir. Yes.
Yeah, this is fine. The next. So, do you think that I think in one slide you have the ratio, right? Enantiomeric ratio, which you got from the from the plot, from the chromatogram. Now, do you think this will change depending on the conversion? Because this was given at 50% conversion. Let's say if I have 40% conversion or 20% conversion, would the ratio change of the starting enantiomer and the product enantiomer? I mean, of the starting compound and the product compound. I mean.
Sir, could you please repeat it? I didn't get it.
So I'm telling that. So this reaction, it was given that. So the chromatograms were recorded at 50% conversion.
Yes, sir.
If I don't let the reaction to go to 50% conversion, I stop the reaction at 30% conversion.
Okay.
How would the chromatogram look like? Would it look like the ratio would be the same, or it will be different?
Sir, I would expect one minute. In that case, the relative areas wouldn't be different, I think.
Okay. Okay, all right, I'm done.
Because there's this ratio here, which is just case law, dependent on K first by case law, not time. So
you can think about it. It's a nice thing to think about. Since you already found the paper, I think you can go through that and then think about that also. Okay, I'm done. I don't have any more questions.
Do any other professors have a question?
I have a question of iron carbon. Oh, okay. Funny. Quick question.
Sir, are you asking something?
Yes. Here, both the complexes are meant to be stable, right? Can you show me the electron count by which you mean that the complexes are stable?
Yes, sir. Ritik, shall I do it?
Sorry?
What? You can say.
Okay. Sir, so in this case, if I consider the eta 1 case, then in here it's Fe2 plus and the number of electrons, Fe2 plus the D shell count is 6. And from the eta 1 we are getting 2 electrons. From eta 1 we are getting 2 electrons. From here we are getting 2 electrons. So what we... 1 moment.
We can calculate from the neutral also. The Fe has 8 electrons, the CH2 giving is 2 electrons, it is 10, and the Ca.
That's correct. Neutral or plus 2?
I am calculating from the neutral.
Ritik, sorry, I got it. I just was confused for a moment. I was just continuing with the charts. So for all these are donating 2 electrons. There are 6 of these, so 6 2s are 12, plus Fe has 6 electrons in its outer shell, 12 plus 6, 18. And
so
then,
how this allylic group donates 2 electrons?
sir, so this is a pi bond here. So this is not donating. There is just a minus charge here. This is an allylic anion, if we consider it. Okay? I think it is an allylic anion. So that would donate 2 electrons.
Was it an allylic anion?
Sir, otherwise, I mean, we calculated it. The EN would be difficult. But it wasn't given in the question, I think.
Yeah, that's what you have to figure out, right?
Sir, but using the EN, we can say that it would be.
Yeah, Sukhdev, can you clarify it? Question.
No, sir. So the question was just an open-ended sort of question where we had provided this sort of an allylic thing, and that's all that they were provided. So it's open for interpretation,
So
and
over
they have
here,
to justify.
Over here, depending on the metal, this allylic moiety can either be radical anion or carbocation also. But for iron, in order to get the stability that Ankon was saying, I think he has to.
EN, 18 electron rule, yes.
When a particular ligand is there, it cannot function either as cation or anion as radical, right? It should typically function as one type of ligand. I mean, I understand either one is possible, but not radical or cation or anion. These all possibilities, they don't exist at the same time.
So this is an anion.
Okay.
So even here it's an anion only.
And can you count the number of electrons there?
Yes, sir. So in this case, it's again, Fe has 6 electrons, and so it's in the Fe cluster. So
I am calculating this. So it is Fe plus. So it has 7 electrons, and I am calculating from the neutral, and from the allylic we are getting 3. This 7 plus 3 is equal to 10. For 4 CO we are getting 2 each. So it is total 18.
Okay, so you're saying it's Fe3 plus and allylic contributes to 3 electrons.
No, sir, Fe2 plus.
But you counted 7, I heard.
Certain order for this charge, I think.
Okay, all right, okay.
Are there any other questions from the professors? Or Shukru is raising his hand for a long time. If there's nothing from the professors, I will let Shukriya ask a question. But we are past time, so Shukriya, please make it fast.
Yeah, so I had 2 quick questions. One is in slide number, slide number 12. You have said the chair form of the reactant is the most stable conformer. So is that the reason why you have considered that in the reaction?
Yes, we are assuming that the chair form is the most stable.
So the most stable form is the most reactive form?
Not necessarily.
Okay. And in another place in your presentation, you have mentioned that the transition state is close to the intermediate according to the Curtin-Hammett principle.
Yes.
Does the Curtin-Hammett principle state that the transition state, if it may be close to the intermediate in energy, then that you can model it as an intermediate?
No, it's just that the intermediate is higher in energy. That's why it's closer to the
it's close. The transition state is close to the intermediate.
So is that the Curtin-Hammett principle? Is that what the Curtin-Hammett principle tells?
It's not higher energy, right, Ritik?
What?
It's closer to the structure with higher energy, right?
Yes.
So intermediate is at higher energy. That's why this transition state is closer.
So that is the Curtin-Hammett principle.
I think that is what I read.
Okay. Cool. And another last question from me. You said that you are using the Felkinan model. Is the Felkinan model sufficient in this question? to explain the selectivity?
Yes, we explained all. Or not.
It is self-sufficient, the Felkinan model. So if you have got an oxygen-containing substituent, then also the Felkinan model is sufficient to explain the selectivity?
Which one?
So here you have got at the center, can you go back to the where you have the carbonyl containing thing, that where you're showing with the carbonyl? Yes. So one of the substituents has an oxygen, right?
Yes.
So in that case, say for example, instead of this particular bulky group, I have a smaller chiral group which is ligated to O. Then the selectivity would change if you are using the Felkinan model, right? So is the Felkinan model just the Felkinan crude model? Is it sufficient?
No, we have mentioned H bonding and steric hindrance.
So like just H bonding, Felkinan model, they are sufficient. You don't need any other like.
Felkinan also not. Felkinan also not talks about the transition state. So I think so. Felkin is not sufficient to describe.
So irrespective of the polarity of the substituent, you can use Felkinan model anywhere.
Polarity of which substituent? Can you please?
So you have got an oxygen here, right?
Yes.
So should we use the crude Felkinan model here?
I mean, if any ligand type of something present, then
okay, maybe look up on the polar Felkinan model. That's okay. That's all from my side.
Okay. I will just.
Okay. I mean, you could have suggested in place of oxygen, like in place of this, what we would have put in, what you wanted to put in here. So.
I just have a couple quick questions. One. In the last question, you have taken out the Cl minus. Why have you taken out Cn minus and why not CO?
Because Ritik, CO coordination is stronger, right? I think CO because of the pi acidic nature.
Pi back bonding.
Okay. Please go to the next slide. Yes, in the second part, why have you taken the 2 protons equivalent? The 4 protons equivalent. I understand that suppose the cis ones are equivalent, but why are the cis and trans ones equivalent?
Because at like I have mentioned this that, and in NMR we sample from discrete data points. So at higher temperatures, this rotation is so fast that the differences between these can't be seen. Like they become magnetically equivalent at the time scale. This time scale. So this is the same thing why we don't have coupling between equivalent protons, like coupling between protons and a methyl, because this J coupling is dependent on electron, like the electron density, and electron density is also present in methyl. But the problem is that the methyl rotation is so fast that it's a self-decoupling mechanism there. Okay. Like we apply decoupling pulses also, and it's the same thing here, I think.
Okay. In the last part of the first question, you have compared CH and CD bond, and do you think the bond lengths have anything to do with the 0-point energy or maybe anharmonicity? You have just taken the centrifugal distortion due to the rotation.
That was like that explained the observations. That's why.
Okay. I'm done. I think we can move on to Team C. Team C is Pravar Kataria and Dev Gupta, right? Okay.
Yeah. Is the slide visible?
Yes. Please put it in slideshow view and we can start.
Yeah, so we start with question number 3, in which we'll both contribute it in presenting, and in the rest question it is one by one individual. So yes, we've done the part 3A. So we first observe that when
Hello, can't hear you.
Yes, Pravar, you're not audible.
Yeah, same here.
Shall I continue in his absence?
Sure. Go ahead.
First, we can observe that if delta is positive, with the Y would be an electron donating group, and if delta is negative, Y would be an electron withdrawing group, because electron withdrawing group would increase the acidity of benzoic acid, and electron donating would decrease it. Now, benzyl halide can undergo both SN1 and SN2, a substitution to both SN1 and SN2 mechanism. So, so for the left half of the graph, where the rate constant is decreasing, we said that it is preferentially undergoing SN2 reaction because the NO2 group would increase the electrophilicity of the carbon, and it will decrease the stability of carbon cation. So it would prohibit the SN1 mechanism. And on the positive side of delta, we said that as the Y group is increasing the stability of carbon cation, it will preferentially go SN1 reaction. Now, in the second graph, now Rahul will take over.
Am I audible?
Yes, please go ahead and please do it fast.
Yeah. Yeah, so we list some characteristics for both SN1 and SN2. SN1, it proceeds with carbocation formation and almost complete racemization. Almost complete because it is slightly excess in the inverted product, and SN2 is a complete inversion. And we also analyze which groups favor which mechanism. So SN1 is favored by electron donating groups and SN2 favored by electron withdrawing groups. So for graph 1, we claim that the part where delta is less than 0 is governed by SN2, and part where delta is greater than 0 is governed by SN1. SN1 and SN2 go hand in hand. So, and in benzyl positions, both are supported. So this could be a possible reason. And the solvent is also neither too polar like homolysis or too like solvolysis, and neither too ionic to support SN2, so it could go both ways. And for graph 2, when the R group is changed, we claim that it goes completely by SN1 or majorly. Dominant part is the SN1 part. Okay, so the R group could either prevent SN2 almost completely or promote SN1 too much. The point one, it could prevent SN2 by being a very bulky group like tertiary butyl or something, and also it can promote SN1 too much by if it is a cation stabilizing group like OCH3 and amides. Okay, so the part 3 where it asks about the log K by K0 for SNAR versus delta. We first claim that increasing the electron withdrawing group, the SNAR rate increases. This is because of the formation of Meisenheimer complex if there are one or more than one electron withdrawing groups. So it goes like this, and this is stabilized if R group is more electron withdrawing. So by the definition of delta, so more the electron withdrawing group, more is the rate, and less is the delta. So we get a graph like this, which has a decreasing kind of slope. It need not be linear, but the nature will be decreasing. We proceed to question 1. Question 1 will be explained by my teammate. Yeah, so I will start with this. The rotational analysis can be done to determine the bond lengths. There are mainly 3 types. This is just the summary of rotation analysis, and chloromethane falls under the category of symmetric top. After finding the formula for rotational analysis for symmetric top, we get this, and substituting the values, it also says that the difference in wavelengths or wave numbers is constant. So yeah, that comes out to be 2b. So, and by calculating, we get the values as 1.781 for CCl and 1.1 Yeah, I think it. Yeah, 1.096 for CH. Also, this is the proof of moment of inertia of IA and IB. This is the proof for IA, the symmetric axis. My teammate will proceed if he has no technical issues.
Yeah. So I assume that the CH bond, three vectors along the CH bonds, A cap, B cap, C cap. So by symmetry, the CCL bond will be along the direction of minus A cap plus B cap plus C cap. So to find alpha, we took the dot product of A cap and alpha A cap plus B cap plus C cap minus A cap plus B cap plus C cap, and I found the modulus of mod A cap plus B cap plus C cap. Then IA would be 3 times MH LH sine square alpha, because the projected length of LH along the plane perpendicular to the axis would be LH sine alpha, and by putting the values we get the desired formula. For IB, if we view from the top, both the H will be coinciding and the projected length would be LH cos theta by 2. So we just directly took individual MR square and added them and got the desired formula. And for the potential energy curve, we approximated
7 minutes.
We approximated my energy function as a double exponential function and found the best fitting curve, and this is what we got. And I have marked the point of minima, which came out to be 1.773 angstrom. And I think the bond length should follow a definite order due to reasons, and potential energy should be the closest approximation, as it just accounts for the energy and there are no distortion due to rotation.
Yeah, in the case of CD and CH bonds, we have we approximated or assumed that due to the electron diffraction, the bond gets stretched due to being bombarded with higher energy. The bond gets weak and stretched, and because the bond strength is low in CH, the effect is observed more in CH as compared to CD. Hence, CH is more than CD than CH actual. Yes. Then I explain the question 2. This is the nomenclature for the rest of the question, so there is no confusion. Then, yeah, so first of all, it was not clear why are the enantiomers acting differently with this reagent, but then we claim that the steric hindrance is the factor because of which one is preferred over the other. Yeah, so we try to find the most suitable attacking morpholine, and we find out that it will be the R conformation, and in which the benzyl ring will be away. This is from the side view, so benzyl ring will be away downside, and this is down from the main group, which lies here. So R would be the most favorable. Yeah, the analyzer. So this is some basic about chromatography method. We actually had to relate the area with the other things, and height. We took no use of height and retention time. The area actually tells the ratio, as it is the area between the rate of detection of material and time. So yes, because we use 0.5 equivalent, so these both ratios should be equal. Otherwise, they might or might not be equal. Yeah, so we define. We calculate the enantiomeric excess, which comes out to be 84%. Then we figure out the mechanism of the reaction. First, it is basically addition elimination, and the first step is reversible because it could come back the molecule, and the second step is RDS, in which the group leaves. The step, it is mentioned here, and the second step is claimed as RDS and supported by facts like that why the reaction is stereoselective, and also the final order is one respect to the substrates. So we find out the rate by using the RDS, KRDS into Zwitter ion concentration, and then Zwitter ion by equilibrium concentration, we get this result. Now we have to find out the energy difference. For this we use the Arrhenius equation, and this is the approximate graph for any acetylation reaction. These are the overlapped graph of S and R enantiomers. Even the intermediates will differ, but they will differ by small amounts, which will not be insignificant in front of the difference in transition states. And so we get this rate, and when we divide this, because K equilibrium is assumed to be almost constant as intermediates energy is almost same. So when we divide this ratio, we get that we get E raised to the power minus delta E by RT. Upon calculating, we get I think it's the next slide. 6.04 kilojoule per mole, higher for S powerful in and lower for R. This difference is shown in this graph. Okay. So I think there's it is done. I think.
Professor, you can ask questions.
So Anubhav, I just have a quick 1 or 2 questions maybe. Okay. So the first question is when you have these potential energy surfaces, right? Which approximation are you using over here? And from your quantum chemistry knowledge, can you tell me which approximations are you using for any kind of potential energy surface? You're considering the nuclei, right, to be fixed. So what sort of approximations you're using? It's a very famous one.
Yeah, I'm unaware of it. Maybe my teammate is aware.
Okay, never mind. So my next question is the free energy profile diagram that you had shown, right? For the last question, for the second question.
Yes.
Okay. So now in this one, you're showing the energies of your starting ground states and products to be same, right?
No, the products is not same. Actually, we made it to be same, but there is a correction. The product is not same. The initial reactants is same.
Okay. Why the product is not same? If the product is let's say the similar, then why the energies are not same?
Yeah, they are diastereomers. They can differ in energy, I suppose.
Where are you getting the diastereomers from? How come are they diastereomers?
Wait, No, maybe they are enantiomers. Yeah, this is achiral nitrogen. Yes.
Can you have a chiral nitrogen? You said it's an achiral nitrogen.
Yeah.
What?
Yes, it is an achiral nitrogen because it's, I think, attached to a amide group. Yeah, this is an amide group, so it must be achiral, I suppose.
Okay, so go back to that slide that you had shown where the free energy profile diagram. Okay, now if I tell you, you have your catalyst. Okay, you have your chiral reagent, right? And you have your reactant. All right.
Yes.
Are you listening? Yeah. Okay. And you have like R and S enantiomers, and you have your chiral reagent. Okay. And if I tell you the ground state energy is not going to be same, can you think of a reason why that is happening?
Ground state energy of?
The ground state, your starting reactant that you have shown it to be similar, right? You have put them same. So let's say if I tell you that it is not same, can you think of a reason?
No, I cannot. I think it should be same.
Okay, fine. Yeah, Anubhav, I'm done. Yeah, someone else can ask.
Professor Mukherjee, Professor Das, maybe Professor.
Devashish, go ahead.
Yeah, maybe because
Hello? Can I ask? Hello? Yeah, I think, So I think in the last question, you mentioned something that you were not clear where is the spurious electrode is coming from, right? You mentioned something that...
Yeah, initially we were uncertain that, where is that? Yeah.
What is the reason for uncertainty?
Yeah, theoretically it looks that when a chiral reagent reacts with a chiral substrate, it should be different. The reaction should be stereoselective. But when we were trying to draw the structures, it were almost resembling. I don't know, maybe mistake by us from our side.
Okay, that's fine. Yeah. All right. And I think somewhere you went for the selectivity. There is an equation you had solved, right? E or something. Can you see that?
Yeah. Enantiomeric axis. Yeah.
Yeah. Where was that? Where are you?
Question one.
No, it will be towards the end. It will be towards the end.
Oh yeah.
Yeah, the blue one. Yes. Yeah. Yeah, I think so. For using this one, you have calculated the enantiomeric axis, right?
Yes.
But did you calculate the selectivity factor or something? The K fast by K slow?
No, we haven't.
Let me ask a quick question. So you guys fitted that curve using some double exponentials. What is the rationale for that?
Yes, sir.
Yeah.
Can you repeat?
What is the rationale for using double exponentials?
First, I tried the rational function like a by x to the power minus b by x to the power n, but it wasn't following the curve really nicely. Then I tried this other one, the other approximation, which I found a very good fit. So I thought this is a better approximation.
But I mean, realistically, what do you think you must have used?
In reality, I first tried with rational, then tried with exponential. The exponential worked, so I just wrote that I took exponential as an approximation.
Okay.
We had some idea of the. Yeah, should I speak?
Yeah, sure. Go ahead.
Yeah, we had, although it was vague, we had some idea about the models. One was that Born exponent, which he's mentioning that irrational functions, but that didn't work out. The next model that came in our mind was this. We actually don't know from where it came. Probably some time back studying, but yeah.
Okay, let me ask you another question. Do you think you would have errors because you've used a different function and probably the potential energy landscape that the atoms are actually seeing is different? Do you think you would have errors in the bond distance that you calculated based on this function?
Yes, you would have. Yes. Because I approximated a little bit the exponents.
Okay. And can I ask how different are A and B, those coefficients that you had in your double exponentials?
Yeah, those are these, I suppose.
Actually, the coefficient, these are not the actual coefficient. The actual coefficient would be when we would split the x plus 1.3065, 1.3605, and then multiply it with the coefficient. But I tried it, but the graph deviated more. So I thought just keep it as is.
Okay. Okay, all right, yeah, thank you.
Any other questions from professors? Otherwise, we can open it to others as well. Okay, does anyone from the floor have any questions? Okay, I have a question for you guys. You have said this order of the the bond length order, and why do you think it is so? Why do you think this order is being followed? Do you think so? What was asked is, is this order systematic? Do you think for every kind of bond this order would follow?
Yeah, I think we are sure that these both will be higher than potential. Rotational and X-ray would be higher than potential, but we are not sure between the order amongst these two.
Okay, have you calculated the electron diffraction one?
No, we have skipped that part.
Okay, so you're not sure whether this is systematic or not, right?
Yeah, no. For the exact
sure
order,
of the fact that potential will be minimum.
Yeah, we are sure that potential will be minimum.
Okay, why do you think X-ray is more than the potential energy measurement?
Because we thought that X-ray might give some energy to the atoms, that is the diametric molecule, so it might increase the bond length from the equilibrium length.
You said somewhere, no, that when you are hitting the molecules with electrons, the energy they're taking in energy, and the bond length is increasing. Yes, over here you have said this, right? So why do you think the energy? Why do you think the electrons that are hitting the molecules will provide them energy and not dissipate energy from the molecules and make them shorter, thus compensating for this any elongation in length?
Dissipating energy, yeah, they will provide them energy, but taking the energy, they can go either side, as seen in this potential energy graph.
Meaning, I didn't understand what you said.
Like, if we drew a horizontal line above the minima, if we gave them some energy, they would be bounded between two distances.
Yes.
So we are saying that the average distance would increase.
So after the electron has hit the molecule, does the electron know what the distance of the distance measured is, and what the subsequent energy imparted to the atom is?
But if any amount of energy would increase the average bond length.
Okay, and after that, if the electron hits it and dissipates some energy and brings it back to the minimum, is that not possible?
I think that is improbable, mostly because this is oscillating and probably damped in the collections. So it will be a very short-lived phenomenon. So electron hitting it twice, it looks improbable.
Okay, I'm done. If anyone else has any questions, they may ask. Okay, if there are no more questions, we can move on to Team E. Team D has bowed out of the final round and decided to spectate. So we'll move on with Team E. Team E is Shayantan Khan and Shubhajit Chakraborty. Please start.
Yeah, hello. Am I audible?
Yes, please share your screen.
Okay, just a second.
This is Team E, right?
Yes, sir. Team E. Team D is not participating in this third round.
Okay.
Is my screen visible? Can you please confirm?
Yes, it is visible. You can start the slideshow.
Okay. Yeah, sure. So So the problem 1A was given. The problem of battery bombs. So we just denoted how we can prepare some bombs. Like we would like to share the solution of problem 1A, which correlates to the problem. Like first of all, we have to get that the base 3 batteries of choice. So we have 3 base batteries of choice. There will be lithium ion battery, sodium ion, and potassium ion battery. So, I mean, the possible discharge products, it is asked to the question, it will be, I mean, lithium oxide, sodium oxide, and potassium oxide respectively. So, next it is asked that what will be the suitable cathode material. So, we think that, I mean, the best cathode material for the remaining purpose would be some activated carbon fibers. I mean, they have some exceptional capacitive performance, a robust electrode for supercapacitors. So we think, and carbon being a non-metal, it will be also generally soft and lightweight. So we will go for these activated carbon fibers as cathode material. Next, we move on to, like, I mean, for the amount of discharge products, what we just used is there's, I mean, Faraday's laws of electrolysis. So we know that W equals to EIT by F, which gives, I mean, here W is the amount of product formed, E is the equivalent weight, and I is the current intensity, T is time, and F is Faraday's constant, which leads us to the next slide. Like, I mean, we get, I mean, for Li2, we get it as 0.56 gram. For sodium oxide, you get 1.16 gram, and from for K2O, we get 1.75 gram. So these are the required amounts for the numerical one. From this part, I would like to handle to my teammate, Shubhajit. So yeah, Shubhajit, please can you just continue on?
So okay, then we were to talk about the detonation factors of the compound of choice that we were talking about. So among the three compounds, oxide compounds that we had taken previously, Li2O, K2O, and Na2O, we think that, or we directed our thought process towards the compound Li2O basically because of the fact that in the compound which has Li as the primary constituent has a very small size, and thus it makes the compound a little bit more compact and small as compared to the remaining alkali metals of choice that we had considered. So it must have the largest energy density, and as a result of which must release the highest energy on explosion. So now if we come across the discussion of discharge duration of the battery setup, then we have the same opinion here as well, and we go with the path of Li2O because of its small size and bond length considerations like that, and due to this, Li2O must be the stabler compound when compared to the potassium and sodium counterparts, and hence would have a higher life, and discharge reaction must take place in a steady manner in case of the lithium oxide molecule, and thus must have the longest duration of discharge. Now we come to the topic of initiation of the detonation of the battery. Now if we look at the basic chemistry that was until going on, the lithium oxide gets carbonated first, interacting with the activated carbon fibers, that thus forming the corresponding carbonate species that is pretty vulnerable to intense physical stimuli, or that can be encountered pretty well. Next slide, please. So if our main goal is to arrange a battery chamber where the reaction of the release of the carbon dioxide from the carbonate compound can be well arranged in such a manner that the pressure of the chamber can be suddenly fluctuated, and also we should look for a source of spark ignition for some kind so as to ignite the mixture and for the possible detonation. And so these were some of the possibilities that we could come up with or anticipate. And now if we want to quantify the explosive or detonation abilities, then we actually tried to figure out the exact quantitative values, and also try to look at the Chapman-Juget model, which is a well-known detonation velocity calculation model, but it was coming a bit difficult for us to get the exact detonation velocity values for the battery bomb, as for us for the lithium oxide compound it was becoming a little bit experimental, because we had to find out all the exact enthalpies of the constituent atoms and also the other necessary parameters, so we couldn't come up with the exact calculation. But we tried to correlate the quantitative approach in terms of the chemistry and the structural properties of the compound that we had previously discussed, depending on the size and the structural features, as it releases the best spontaneous energy
So it must have the highest detonation capacity, and hence the detonation velocity be also should be more. So then we were asked if we would make the bomb or not. If we come at the ethical issues, then we should make the bomb as we are encountered or entitled to do is very. We were assumed to perform for the special forces or the very confidential purposes to serve our national forces. So in that sense, in spite of being a very detonative or explosive compound, we should prepare the bomb in keeping the scientific spirit as well as the sense of morality. That's all. Then we will continue with the second question. So in this, the provided reaction is stereoselective because it leads to the formation of two different enantiomers on the attack of morpholine nucleophilic moiety to the given carbonyl center of the chiral reagent. Now, as per the attack of the morpholine, fashion of attack of the morpholine derivatives actually determines the type of formation of the two products. So we basically get that these two products that are given below. Next slide, please. Now we couldn't come up with any better model, but to consider the, as we can see that the phenyl ring and the cyclopentane moiety that we consider to be on the plane, and the rest part of the molecule of the chiral reagent was assumed to be given to be that it was below the plane. So
7 minutes.
For this whole molecule, we considered that if the benzyl moiety is at the axial position, then we would have the less steric hindrance, as it is shown in the first case for the morpholine chair conformation. So we considered the top or the product in which the benzyl is coming to the top face to be the major product. Only due to the following reason, that it would face the less geometry related or steric stability problems, less steric stability problems. Next slide, please. Then we found out from the chromatograph, and we took the area considerations, because from the chromatographs we can argue that the higher peaks for the amide one, for the amide chromatograph, for the higher peak and the higher area would correspond to the major amide product. So we considered the percentage yield for the first one as to be 92.26, and for the product minor one, we calculated the yield to be 7.73%, and that would account for the formation of the two products, and we assumed the maintenance of the first order kinetics in these calculations. So the yield calculation shows that product A is the major product, and for the RDS or the rate determining step, since the morpholine derivative attacks at a bulky group at the carbonyl center, so it must increase the activation energy, and hence it should be the rate determining step for the reaction. Next slide, please. So we could come up with this probable reaction coordinate where the reactant is shown and the rate determining step is shown. And for the product A, the transition state attains a lower energy, and for product B, it attains a little bit of higher energy, but we couldn't come up with the exact values of the transition states for the products, for the transition state energy levels. So we assumed this and found out in approximated energy difference between the molecules, which can be shown in the following slide. Then next slide, please.
Yeah, so thank you, Shobhajit. And then we just move on to question number 3b, which just, demands an organometric stuff is given, which is, FeCO4Cl connect to an Ally ligand. So it just shows two graph, 1H NMR spectra at 70 degrees Celsius and another 1H NMR spectra at minus 30 degrees Celsius. So basically the prime difference which we can see between these two is that 1H NMR spectra at 70 degree contains one quintet and one doublet, and that of minus 30 degrees Celsius contain triplet of triplets and two sets of doublet of doublets. So first of all, we have to see that which constitutes the H atom. So it is basically the Ally ligand C3H5 minus. So now we can see that there are 3 types of H atoms in the allyl ligand, which is shown in the diagram next page. So in the next page, the left side terminal will be HA, the central will be HB, and the right side will be HC. So in this state, we can clearly see that there is a sort of delocalization of electrons. So we can say that, from that n+1 rule, the multiplicity is 2, which for that doublet, the multiplicity is 2, which follows that each of that HA and HC atoms is coupled to exactly one H nucleus. So it means that it is dissimilar to one of the one H nucleus, which is the HB atom. And when there is the quintet, the multiplicity is 5, so it follows from the n+1 rule that the HB type atom is coupled to exactly 4 H nuclei. So they are HA and HC. So we can see 2 sets of H and HC could correspond to 4 H nuclei. So, and on the other hand, at minus 30 degrees Celsius, we can see that 3 sets of atoms, H, HB, and HC. There are 2 sets of 4 surpeaks, which is 2 doublet of doublets. So there are 3 couplings for each of the set of H and HC type atoms, and we can we can see that there are 3 other H nuclei, which is 1 HB and 2 other HC atoms. So, and the similar set of coupling is framed for HC atoms. So from this diagram, we can easily say that on the other hand, where there is a triplet of triplets, so there are 3 sharp peaks, which indicates from the n+1 rule that the HB atom undergoes coupling to both the HA and HC type atoms. So we can, it proves from the Pascal's triangle, the resultant NMR spectrum will frame in a basis of triplet of triplets, which there is 1 triplet of triplet and 2 doublet of doublets in the surveyed 1H NMR spectrum at minus 30. So what we gain from the experiment is that, energy matters, because at 70 degrees Celsius and at minus 30 degrees Celsius, we get 2 different NMR spectra because of the, the lesser the chance of delocalization at minus 30, the different graph we get at that temperature. So that's the representation.
Professors?
So I can start. So the last part, how do you explain the 2 different NMRs? I did not get that one actually.
Yeah. So can I start, Professor?
Yeah. So at minus 70, at minus 30, you see one particular NMR pattern, and then 70 degree, you are seeing another pattern.
Right. Of course, I can explain. Can I begin?
Yes, please.
Yeah, so at 70 degrees Celsius, which can see that there is enough heat energy, which accelerates the rapid bond vibrations. This in turn lead to the delocalization of electrons. And at minus 30, which is a comparatively lower temperature, that heat is not present. So we can say that it doesn't have some energy to possess the delocalization of electrons, which in turn makes that, in this diagram, you can see that.
Just one second. What do you exactly mean by the delocalization of electron?
It means that the bond is shifted. The negative charge that just falls in conjugation with that pi bond.
So this allyl anion is bound to iron, right?
Yeah.
So then what sort of delocalization you are referring to? Because the negative charge is not really free. And if you see the complex, it is actually bound to iron, right? So all the 3 atoms might have connection to the iron. So what is the origin of, how the temperature difference is affecting the NMR spectrum?
Yeah, okay. Right, because the compound is, not exactly, the simple allyl ligand. Okay, so I have a short question, can we just, hypothesize it as an isolated part, like allyl ligand, and can just proceed? Or
no, then
I can be wrong.
Then you won't be able to explain. If you remove this allyl from the iron, you will not be able to explain.
Right.
Okay, yeah.
Yeah, so
since Sir is asking this, I will just add something over here. Why have you said that HA and this HC, they are different protons? Why are these not equivalent? They look completely
of course. For 70 degrees. Yeah, can I start?
Yes, please.
Okay. So at 70 degrees Celsius, what happens? I mean, there is enough energy according to my answer, what I have done is that, so active delocalization of electrons because of the heat energy provided at 70 degrees Celsius. So we can see that, I mean, those C1, I mean, that Ca and C, I mean, the left terminal carbon and the rightest terminal carbon, those are equivalent to each other because they are just, I mean, resembling to canonical forms in that allyl ligand. So we can similarly say that the corresponding HA and HC will be equivalent to each other at 70 degrees Celsius.
Why is HA and HC not equivalent? Because they are just mirrored.
Those are at minus 30 degrees Celsius.
Why is it not equivalent?
Because there is not some active delocalization of electrons. There is not such.
So you're saying the charge is localized in C minus, right?
Right, at minus 30 degrees Celsius.
There is a double bond delocalized.
Right.
So there are many such molecules in your sample, correct?
Yeah.
So in some, suppose C1 there is negative charge, in some C3 there is negative charge. Is there not averaging while your data is being collected?
Yeah, that is one thing. Another thing is that, do you think the electron delocalization, does it depend on the temperature?
Yes. Do you think benzene is less aromatic at low temperature, more aromatic at high temperature?
No, not like that. Yeah.
So why are you saying that due to your heat energy, thermal energy, delocalization is increasing? Where have you seen such thing other than your supposition over here?
I can explain. I mean, on the basis, like, I mean, aromaticity. In aromaticity, there are, I mean, all the canonical forms are same, but here, if there is, okay, so yeah, this just contradicts my point.
No, here also they are same. If you are writing the two canonical forms of allyl anion, they are actually identical.
Right, exactly.
Yes, sir. Sorry for interrupting.
No, I'm fine. I'm done. Yeah.
Okay. Any other judges? You can ask questions.
Can you ask a quick question?
Yes.
So in your this free energy diagram, you had shown the difference to be 20 kilojoules per mole, right? So you were just taking that like just roughly, okay? So can you tell me like how much this is a kinetic effect or is it a thermodynamic effect, right? It's a kinetic effect, correct?
Yes, ma'am.
So can you just roughly guess? I mean, maybe you don't know what energy difference do you need, let's say, to get 99% EE? Or predominantly 1.9. How much do you think it should be around? Should it be 20 kilojoules that high?
No, ma'am. That was actually as we couldn't come up with the actual calculations. Just we showed the difference, but it shouldn't be that high. Actually.
Okay. So how low can it be then?
I guess it would be. Around 8 kilojoules or 9, I guess.
Okay, if I tell you the difference is 1 kilojoules per mole, is that sufficient?
For the no, I guess it should be a little bit more, I guess.
Should be a little bit more. Okay. Do you know the relationship? How can you estimate that?
No, not exactly.
Okay.
No, not exactly.
Okay, and in one of your slides, you had shown this. Go to the previous slide where you're discussing these enantiomers, why one was reacting favorably and the other one is not.
Yeah, I think.
So in your product A, this simply it can ring flip, right? So why is it in the axial position? I didn't get it. Ring flip can happen, right? It's a simple conformational change.
Yeah. We just we accounted for that fact, but we couldn't come up with the exact model for that. But we considered just the steric fact and nothing more than that.
Yeah, that is fine. What I'm asking is, will ring flipping change your configuration? That's what I'm asking. I mean, you can simply draw it. You have drawn it in an axial one. Can it be equatorial also?
It can be on the other side of the nitrogen, in the equatorial position, but on the other side of the nitrogen. That will be the enantiomer.
Yeah.
Isn't it?
Yes.
Okay, Anubhav, I'm done here.
Okay, ma'am. Professor Fani, do you have any questions regarding the battery bomb question?
Yeah, can I just quickly ask? So, guys, you did not calculate or you did not do the chemical titration part of that question. Did I get that right?
Yeah, exactly. Like we couldn't come up like of that question.
Okay. And then the next one is discharge products. You've considered only the three complete oxides. How about, did you consider any other oxide products?
No, sir. We think these three oxides will form only, according to our intuition.
Okay, no other oxides?
I think there will be no other.
Okay. Okay. How about, why did you rule out something like a peroxide or a superoxide?
Yeah. So what happens basically, like in that when it just reacts with oxygen, so it just forms simple oxides. So I think lithium, sodium, and potassium oxides will form only.
Okay. All right. Sure. Another question that I wanted to ask. 1 second. Yeah. So you talked about unable to quantify the heat released. Did you try to look for enthalpy numbers for the formation of carbonates?
No, actually we tried to, but we couldn't come up with the actual calculations for that. We tried to calculate the enthalpies of the respective carbonates.
Okay. Yeah, sure. And the last thing regarding the initiation of the reaction, can you be a little more specific? I think I did not understand how you are planning to initiate.
Yes, sir. Yes, sir. I can explain a little bit more. As I was going through a citation, it told that for the lithium carbonate species that we encounter, so these species, it told that are pretty vulnerable to the physical stimuli like pressure, or either we can set up the batteries in such a way that we can arrange a piston system inside the battery to increase the pressure suddenly, or we can arrange for an spark plug that ignites the mixture, that provides the amount of energy to help the carbonate to release the carbon dioxide and release the energy for detonation. That was the main we thought about this idea only after going through the citation.
Okay. All right. And one last question: did you consider the electrolytes that are of interest for you for this battery at all?
I think Shayantan.
Yeah, sir. Can you please repeat the question once?
Did you consider any electrolytes of interest for making this?
No, sir. Actually, no specific. We didn't. Think of the electrolyte specifically. So no.
Okay. Okay. All right. Yeah. Thank you. Anubhav, I'm done.
Are there any questions from the judges, or perhaps from the floor?
Yeah, so I would like to go ahead with one question. So just two questions. So this 20, 40, these numbers are like you couldn't calculate. So like these are just random numbers.
Yeah.
Just a second. I'm going with the slide.
Just approximated these ones.
No, approximate means there should be some basis for approximation. But is it an approximation or it's a random number?
No. These are just randomly taken up. But this
and
should
just
be
subtracted one from the other. Okay, cool.
Yeah.
And in the previous question, just the previous slide, just the previous slide. Could you go to that? Yes. So in this, you have product A and product B. You are analyzing the stereochemical output of the reaction. So in you are saying that product B, you have written that it faces some geometry stability problem. I didn't get that part of it. And also in product A, the CH2 pH group is in the axial position, right? So it should be minor conformer or major conformer.
I mean, the geometry stability problems, like we wanted to convey that we were talking about only the steric factors
okay.
by these terms.
Yeah. That is fine. That is fine. So what kind of steric special interaction is there in B which is not there in A? Which
I
this
mean
favors B?
that I mean that if that part, apart from the phenyl and the cyclopentyl part, if we consider the bottom faced part of the chiral reagent, then I consider the interaction of the nitrogen negative charge with the carbonyl center, but I tried to see that there may be the presence of the interaction between the oxygen lone pairs of the the next oxygen to the nitrogen atom that it is shown here. Then among these oxygen lone pairs and also the equatorial CH2PH benzyl group, and which may be a little bit less in case of the axial portion. Axial
But the axial conformer is the minor conformer, right?
Yeah. We looked at this possibility, but we couldn't come up with the better model, so we just considered this one only.
Okay. So there is no other specific reason why you are considering the minor conformer.
No.
Okay, so the major conformer should have been considered.
The major conformer should have been considered, but we couldn't do that.
So you came up with the minor conformer. So in ideal cases, we should only consider the major conformer for understanding the transition state. This is what you're trying to say.
Right? This can vary also, that we need not take the major conformer always for analyzing the product formation in these cases, but here specifically due to this reason we had to take the equatorial conformer.
Okay. Thanks.
Are you done, Shukri?
Yeah.
Okay. Then we can move on to the final presentation of the day, that is by Team F. Team F constituting of Shomodipto Vishash and Sharota Shah.
Yes, you'll be starting soon.
Okay. You can unshare your screen. Yeah. Okay.
Is my screen visible?
Yes, please begin.
Good evening, everyone. I'll be starting with question 1B. So this was about chloromethane and analyzing different spectra generated from different spectroscopic methods. So here we apply the symmetric top model, also known as PROLATE. So as per this model, it has two rotational axes with same inertia, which are the degenerate axis, and one with different inertia, which is the unique axis. So they have been designated different symbols. We are accounting here for centrifugal coupling terms, and considering all that, we have framed this equation where BE is the rotational constant of the unique axis and AE is the rotational constant of the degenerate axis. As given, J is total rotational angular momentum and K is total angular momentum along the unique rotational axis. So from the data given of a particular energy transition and the general line splitting, we find out what we get two equations relating AE and BE, following which we can determine what the specific values for AE and BE will be, which is what has been done here. And there were further equations provided relating IB to the bond lengths and the bond angles involved. So the calculations have been done here, at the end of which we determine the length of the carbon-fluorine bond to be 1.737 angstrom. So the next part of the question deals with electron diffraction spectroscopy. As per the principles of electron diffraction spectroscopy, the resonance condition occurs when the electrons are ejected at a distance from the central atom in the molecule which is equal to that of its neighboring atoms. More massive the atoms in the molecule, greater is the corresponding intensity. Based on this, studying the data given, we can identify 3 peaks occurring at distances of 1.11, 1.779, and 2.381 angstrom. The figures in brackets denote the corresponding intensities given by the radial distribution function. The first peak gives a CH bond length as 1.1810 angstrom. The second peak gives the CCl bond length as 1.779 angstrom. The third peak, I think, corresponds to the distance between chlorine and hydrogen. It has a lower intensity since it describes a through-space interaction. From the potential energy surface, we see that the carbon-chlorine bond length is 1.774 angstrom, since this corresponds with the minima in the potential energy curve. Now, coming on to error analysis, the discrepancies in obtained data and the pattern of the same would suggest that the associated error is mostly systematic, though some of it is down to random fluctuations. Since electron diffraction spectroscopy requires vacuum conditions, there can be perturbations there and fluctuating incident intensities and so on. Since the error starts for lighter species like hydrogen and drops low for the heavier species like chlorine, relating this with the compatibility of heavier systems with EDS, one can say that this is overwhelmingly systematic. For X-ray diffractions method, it is required that the sample crystal is homogeneous in nature and there's a lot of it available, otherwise the X-ray diffraction won't be sensitive enough. For rotational spectroscopy, since the bond length isn't directly available from the data given and one has to refer to further theoretical models, which are based on reasonable approximations, but nonetheless these approximations will accumulate and this will create further error. So for this species, supposing there is enough of it available and it's fairly homogeneous in nature, X-ray diffraction spectroscopy is most suitable. But obviously one cannot say this in general because all 3 methods are widely used in different contexts depending on what kind of system we are dealing with. Now coming on to relative precision of CH3Cl and CD3Cl in electron diffraction spectroscopy. As elaborated earlier, more sensitive the species is to a certain spectroscopic technique, more precise will be the corresponding spectrum generated. Heavier atoms are more sensitive to EDS as they interact more prominently with the diffracting electrons. Hydrogen being the lightest there is, it isn't ideally suited for this method. Deuterium, on the other hand, is the heavier isotope and will yield relatively precise results. This does account for the relative precision of CH3Cl and CD3Cl. Moving on to question 2. So this is about the stereoselectivity as observed in acylation of this morpholin derivative. This morpholin derivative, it acts as a potential base. It can lose this proton, whereas while the lone pair on nitrogen will abstract this hydrogen present in the chiral reagent, which on the other hand will undergo further delocalization of electrons to ultimately attack a different molecule of the morpholin derivative. A lone pair, the negative charge nitrogen, thus will attack, there will be a nucleophilic attack on the acyl carbon, due to which ultimately this acylated product will be obtained. Now, since there is steric hindrance caused by the by the ring system located below the plane, only a particular orientation of attack by nitrogen will be favored, due to which only a particular enantiomer of the morpholin will be participating in the reaction. And since the lone pairs of nitrogen cannot undergo inversion here, since it's fixed to a ring, this will result in selective reaction. So unfortunately, I couldn't refer to any model for this. So this is simply a rough sketch of what I think the major product will be. The point is the benzyl group alpha to nitrogen here will remain above the plane, whereas the acylated group, which has been introduced, will be located below the plane. I'm not particularly familiar in dealing with chromatograms, so I'm not sure about the data I've got here, but it's not random. So based on what I think is a fraction of the other enantiomer which reacts, I've referred to the Boltzmann distribution here to account for the energy difference between the transition states of the two enantiomers of the morpholin derivative. So the next part, which is question 3b, will be discussed by my partner Somodita.
Am I audible?
Yes, you are.
Yes.
Go ahead.
Yes, you are.
Yeah. Here we can see in this question iron forms an octahedral complex with the allyl ligand, and the anionic ligand binds in. We would see that we will ultimately explain that why it binds in eta 3 fashion in the higher temperature and why eta 1 in the lower temperature. And the carbonyl ligands chiefly act as a spectator ligand, so it doesn't serve any purpose as perfectly. So change the slide. So here we can see what an delocalized allylic ligand looks like. Here the terminal protons, they are all similar in nature and they are in a similar environment. So they are, the terminal 4 protons are enantiotopic in nature, marked as HA. Hence they give one signal and the central proton gives one signal in the non-delocalized part. Now the terminal hydrogens are in two different environment, like here in the non-delocalized part. Here we can see if we take let's assume the allylic ligand is not delocalizing. So here we can see the minus charge on carbon, the two hydrogens can be marked as HA and the other ones HC and the middle one as HP. So here's the same thing is done. Change the slide. Now NMR at higher temperature, now we can see there are 4 protons gives a doublet. Now from the 2ni+1 rule, we can see how it gives the 2 signal due to the neighboring hydrogen in the center, which is relatively upfield. Now the central hydrogen gives a quintet from the 2ni+ rule due to the neighboring 4 protons. So on each side we get 5 signals because the coupling constant of each neighboring is same as they are same in nature. So 3J coupling is, we are considering the 3J coupling also. So according to Pascal's triangle, so we can see the intensity of the quintet would be 1:4:6:4:1, and it would be and the doublet would be 1:1. So here we can see that the central proton is having less dense electron area, so it is relatively de-shielded and appears and has more ppm value, while the terminal hydrogens, it has more electron dense, so it appears to have shielded. Change the slide. NMR at lower temperature. Now all the terminal hydrogens are no longer identical, marked as HA and HC in previous slide we have seen. Now the central proton, being the de-shielded one, is the most downfield and gives a triplet, 9 signals, because they are in the different environments. So 2ni+1 and 2ni+1, so 3 into 3 gives 9 signal. And here also 3J coupling we are considered. So the olefinic terminal hydrogen is HC is mid in the spectrum and gives a double doublet due to the central hydrogen atom, again due to 2ni+1, 2 signals, thus giving 2 signals for 2 protons. Now the HA is the most upfield, hence gives a double doublet for the other 2 hydrogens. Here we can see in this case the terminal hydrogens are no longer similar environment, so the coupling constant would be also different. So here we can see the splitting occurs, and hence we get the 9 signals, not necessarily the 5 signals, because the coupling constant A is different from C, so we get a different 9 signals. That is what. Change the slide. Now the mechanism. Now let's come to the mechanism. At higher temperature, delocalization occurs so fast that the NMR spectrometer can't identify the definite structure. By definite structure, I mean a specific resonating structure in it. Therefore, the terminal 4 hydrogens are identical and gives a quintet signal. At lower temperature, delocalization doesn't stop, but the speed at which delocalization happens is reduced in such a way that the NMR in the NMR time scale that the resonating structures are trapped. By trapped, I mean detected, like they are not detected and identified by the spectrometer. Hence, we get a different signals for the respective terminal protons, one for the olefinic protons and other for the protons in the charged carbon atom. So it can be arguably said that at lower temperature, complex binds through anionic carbon, that is eta 1, and while in the higher temperature, it binds through the iron to 3 carbon atoms, that is eta 3. It can be interpreted in such a way. Change the slide. That's it for my type. Thank you.
Professor Garima, would you like to go first?
Yeah, sure, Anubhav. So, Swagato, right? Yeah. In your second part, where you're showing the product. Yeah. Yes, here. Where is your chiral center over here?
It's supposed to be on the nitrogen because the lone pairs cannot invert since it's fixed to a ring.
Really? Is that where the
There's also a chiral center on the adjacent carbon.
Okay, do you think that nitrogen is chiral?
No, it isn't chiral. No, that would be the wrong thing to say.
Sorry?
No. It's not chiral.
It's not chiral. So that means the product that you have shown is wrong, right? So you've not taken into account the carbon chirality over here, right?
Yes, I couldn't refer to a stereochemical model for this. Yes.
No, stereochemical model is fine. You leave that. I'm just asking about this compound. How is it chiral? That's all I'm asking. Okay, can that nitrogen be chiral under some circumstances? Like, you substitute with some other groups or something like that? Do you think?
If we are talking of invertomerism, then it can be inhibited if it's substituted with bulky groups, which prevents rotation or flipping of the nitrogen lone pair.
Okay, and any other way, let's say, what if we have an ammonium salt? Can that be chiral?
Yes, it's capable of being chiral then.
Sorry, I did not get you.
It can be chiral then, yes.
Okay. And can you go to your first part?
Yes.
Okay, first part was okay, go to the second one. Okay, third, maybe where have you determined this from the potential energy surface? You would have got a bond length, right?
Yes, ma'am.
So what's the bond distance that you got from there?
It's 1.774 angstrom.
Yeah. So it's the same question that I think I asked the last group also. What is this potential energy surface? What is approximation?
Well, I think we have used the Born-Oppenheimer approximation. I mean, it's one of the approximations that is used.
Okay, good. So what is that Born-Oppenheimer approximation?
It's that, there is no coupling considered between the nucleus and the electron. So the nuclear component, it's left out.
Nuclear component is left out, but you are varying the nuclear coordinates only, right? On your potential energy surface, isn't it? What are you doing? You're changing the distance between the nuclei, isn't it?
Yes, ma'am.
Then? Okay, Swagata, think about it. Anubhav, I'm done here.
Okay, ma'am. Other judges, if you have any question.
Yeah, just one thing. I think when you sorry. Okay, just one short thing. I think the next slide or the one after, when you have calculated the stereo selectivity, the non-stereo selectivity. Yeah. So, what is the percentage that 0.3 by 4.58? What is this? Did you take? Yeah.
Yes. I'm not used to chromatograms, so I just interpreted it as I could. I'm not sure about this figure.
No, generally, when you forget about chromatogram, when you when you have a graph, so do you typically take the area under the curve or height, or what do you take typically?
They are equivalent, but I think area should be more accurate. But I've taken height.
Right. Yeah, I think that was wrong because of that, I think the energy difference what you got is 4.89 to 10 to the power minus 21 joule.
Yes, sir, but that's that's not for 1 mole of the substance. So then it would be multiplied by some factor of 10 to the power 23, I think.
Oh, this is for 1 molecule?
Yes, sir, I think so.
Oh, okay. Fine, yeah. I'm done, yeah. Thanks.
Other professors? One quick question on your structure of iron carbonyl complex.
Sir, you're referring to question 3b?
Yeah.
Okay.
You have nicely drawn the structure, but is there any specific reason why you have the chlorine opposite to the allyl group? Or chloride opposite to the allyl group?
Somayita, do you want to answer this?
Actually, I was muted. I was answering for the whole time. I'm sorry. Actually, I assumed that the iron carbonyl bonds, they are very strong. So this system would preferably have the chlorine and the allylic ligands in the trans positions where it can like go any.
Yes. Bond is stronger. Is that the reason? Is it even the correct structure?
Sir, I could not hear you. Please, can you say a bit louder?
Yeah, is it the correct orientation, or is that the reason that you have shown or said is correct? Just because iron carbonyl bond is stronger, is that the reason?
So another reason can be ascribed to this by saying that if it were if the allylic ligand were in the equatorial position, then there could be a possible steric hindrance between the other groups also. So it would be better in the axial position.
Not quite right. Anyway, I think I'm okay. All right. Yeah.
Anyone else?
Can I ask a quick question? Hey, regarding that question on the carbon-chlorine bonds, right? You saw those errors between different techniques. Now, if I were to do the same measurements under extremely low temperatures, for example, if I do a cryo-electron diffraction or a X-ray diffraction when the system is cooled to an extremely small temperature, would you see any differences? Do you think they might be closer to the theoretical values for any reason? Okay, was I audible?
Sir, can you repeat the question?
So the question is, if you were to do these measurements, electron diffraction or X-ray diffraction, while your the molecules are at an extremely low temperature, would the systematic errors, would they go down by any chance? Or do you think you will still have the same systematic errors?
So at lower temperature, it would behave more like a quantum system and less like a classical system. So that might make the results more accurate.
Can you elaborate a bit more? What do you mean by a quantum versus a classical system here? And why that has anything to do with the bond distances?
As in the higher excited states won't be occupied as such.
So you're saying the fluctuations between the bond fluctuations you think are negligible at low temperatures? Is that why you argue that the errors will be negligible?
Yes, sir.
Okay, yeah, that's fine then. So that's it. That's the question that I had.
I want to ask something. Can you go to where you have calculated the rotational spectra? is the
Yes.
selection rule? What is the selection rule for microwave spectroscopy for symmetric top molecule?
Delta J is equal to plus minus 1.
And there is another quantum number. What is the selection rule for that?
And
Okay, so that selection rule is yes.
Yeah. Please say
Yes,
that
it is.
again.
Yes, what is the selection rule for K?
Yeah, that should be 0. K.
Delta K should be 0. But when you have calculated delta over here in your calculation, I can see that you have taken Ej plus 1, K plus 1 minus Ejk. So you have taken delta K equal to 1. Right?
Yeah.
So your entire calculation here on is incorrect. So your delta should come as 2b into j plus 1, right? As in 2b, your delta should come as 2b. It has come as 2a.
Actually, I was putting the value of epsilon 1 was given, so I was actually putting the value of j in k is equal to 1. So in that way, I calculated.
But you did not need the epsilon value, right, for this, because you just had to take the difference between the epsilon j plus 1 and epsilon j.
Actually, I took the difference between the jk and the j plus 1 and k plus 1 spectrum, and I was like getting used to the equal spacing that was performed,
Yes,
and the equal spacing came to this one. Like,
but that k plus 1 you cannot take because that is not allowed symmetry by symmetry. So del k is necessarily 0 for this. Okay, Shukriya, you are raising your hand. You can ask.
Yeah, so I heard a couple of terms here. So you've talked about something called the speed of delocalization. So what is speed of delocalization?
actually, by speed, I meant the delocalization here is rapid. Like as the temperature is high, so
what does
electron.
What does that mean?
That means
delocalization is it is you understand the concept of delocalization, right? Delocalization does not mean that the electrons are like shifting. Those two structures have independent existence. Delocalization means that it's a hybrid structure which exists, and it is none of those structures. But what does the speed of delocalization mean in that context? That is what delocalization is, right? That both the canonical structures, none of them have existence, and what exists is a resonance hybrid. So in that case, what is the speed of delocalization?
By speed, I meant that the structures that we were formed in the I gave an example. Sagoto, can you move to that slide where I drew the specifically olefinic and the that part one? The previous slide. This one. So what I meant is that you can see the olefinic double bond and the negative charge. What I meant is that this structure we cannot find in the higher temperatures because the delocalized, because if it is delocalized, it would not be found. But in the lower temperature, it is that NMR time scale like it reduces, so we can like get a idea that can form in the lower temperature.
So that is delocalization. So in delocalization, the negative charge is moving from one place to the other. In one structure to the other, from one realistic structure to another realistic structure, the negative charge is moving from one atom to the other. Bonds are breaking, bonds are forming, so you need energy for that process. Is
not
that
exact.
What is delocalization? Then what does the term speed of delocalization mean?
By speed, I meant is that like in lower temperature, what we can see is a change in spectrum. So in order to explain the change in spectrum, what we can say is that we see that the no longer a quintet is formed. There is a triple triplet.
Yeah,
so
that is okay.
what could be I understand what you said, that the delocalization is not that realistic like negative charge is moving to the other end. It is not, I understand.
Yes.
But in order to explain it, what I must say that since we do not get a quintet, we get a triplet. So what we can assume that this could be a plausible, but this is not the actual structure. So what we say is that in the NMR time scale, if we reduce the temperature, then what can be said is that the delocalization speed is not the exact word. I might fall short of an exact term, but I mean I cannot express the term I am saying. So what I mean is that this is not the exact structure, but in the lower temperatures, what exactly happens, we do not see no longer a quintet. So in order to explain, we can assume that to get a like triplet, this could be the only possible like things.
Okay, so maybe look up on what is fluxionality. That might help in this context. And can you go to the slide on that you calculated the energy difference between the two transition state using the Boltzmann approximation? Yes. So in this, you said something in response to Professor Mukherjee's question that this is for what is this delta E? Delta E is the difference between the two transition states.
Yes.
So you said in some context that this is for one molecule. So for 1 mole, you have to multiply by something. I didn't get that point actually. I mean, if the difference between two transition states is something, you have to multiply that by Avogadro's number to get something else. I mean, difference between two transition states is always the difference between two transition states, irrespective of mole or whatever. Like you will multiply by the number of molecules to get the difference. Like, is that ever done when we mean that the difference between two electronic states is say 4 electron volt? So does that essentially mean that when you are calculating, you are multiplying? That's the last thing. Yeah, I think we are over time, right, Anubhav?
I was wrong. Yes, apologies.
Actually, Shukriya.
Yeah.
Professor Mukherjee was actually referring to the value in kilojoule per mole. That is why Professor Mukherjee was saying that why is this value so small? That is why probably he had said that we have to multiply.
I think Shukriya is right. Actually, Shukriya is right. Whatever he's saying. I didn't want to elaborate on this because since you were not giving answer to any of them, I didn't want to elaborate. But Shukriya is right. I think this is whether it is a kilojoule or joule. I mean, even if it is kilojoule, it will go down a little bit only, but it will be still 10 to the power minus 18. So.
And we never multiply the difference between two energy levels by the number of molecules to get the difference.
You're right. The final round, I would request the participants to stay here while the judges go to the judges channel and we can discuss the final scores. So judges, I would request you to join the meeting in the judges channel and leave this meeting for now.
The participants, all of you are here? I think most of them are here. Yeah.
Yes, sir. Yes, sir. I think most of them are here.
So how did you guys enjoy the party? I'm asking the participants now. I understand it could have been more fun having you guys here and interacting with you in person, but unfortunately we can't do that now.
The questions were quite nice, sir. So even in the first stage, the prelims, and then over these 2 days, preparing so many different questions for all the 6 teams.
Yeah, I mean, the judges didn't do much. I think it is all our unique students. They have done that. So all your organizers, they have done that. We had no contribution there.
Oh.
Or if at all, very little. So. So are you guys at home now, or you are in your respective institutes?
IIT students are currently at their homes.
Okay.
I heard that ISC called its students back to the campus.
ISC, yeah, some batches are here. Well, most of our students are here actually, yeah. So since how long you guys have been at home and doing the online classes?
Since the time we got our admissions, so we have never been to campus as students.
So like, so you are Aditya, right?
Yeah.
From IIT Bombay?
Yeah.
So, okay, so since August last year you got admitted and then you have never been to the campus yet?
November,
yeah.
Oh, it was November, okay. That's very unfortunate actually. I think.
Yeah, for us, for the Isaac Kolkata students also, we have never been to campus actually, since we got admitted.
Yeah, it's unfortunate because I think the exciting part of studying in these institutes is the campus life. I mean, both in the hostel and outside the hostel, in general, campus life. I think that's the most exciting part. But yeah, I'm sure situation will probably improve in the next months or next year. And since you guys are 4-year or 5-year, sorry, not 4-year, 5-year undergrads, you will have time to be in the campus and enjoy the campus life. It's actually most of the places where they have the students who are part of this 2-year program, like a 2-year master's program and things. They were the unfortunate one. And I think those who joined in 2019 and graduated this year, they could stay in the campus for only about 1 semester, and that's it. And rest of the time, I think they have stayed at home. It's It's almost becoming like a correspondence course, which is not fun. So ISAR and IITs, as you are at home, how the labs were being performed?
They got cancelled.
So no lab, not even online?
No.
Oh.
No, in our cases.
Sir, I mean, for ISAR Kolkata cases.
Sorry, okay, ISAR Kolkata guys, go ahead.
Yeah. So we have actually virtual labs. So I don't know why. I mean, the feeling is totally, not there because on-campus labs. Nothing can be compared to that. So yeah, it is doing. The least can be done.
Yeah. Orpon, you were saying something.
Yeah, if it counts for anything, computer science labs are there.
Yeah. Okay. Yeah, I think chemistry lab with a recorded video, it doesn't give you you don't get any feeling at all actually.
Some of my friends, although they reported a software, so they So their institute conducted titration. So supposedly in that software it simulates you pouring the liquids out of the beaker, and then it programs errors into your values, so you cannot do it once. So yeah.
Oh, that's interesting. Yeah, I think Aisha Kolkata, there is one faculty member, Subhajit Bandyopadhyay, he had an app. I think that detects the endpoint of a titration pretty accurately. You can use a mobile phone because many a times, particularly if some students they have a color blindness. It's not very common, but yeah, people have that. So they don't find the endpoint. So this app actually allows you to detect the endpoint accurately.
All the IITians, are you all chemistry majors or something? Or from other streams? Someone from other streams here? Last year we had computer science majors as well.
Oh, really? They are participating in Chemenigma?
Yeah. So last year we had computer science majors participating in Chemenigma and winning the second prize as well.
Wow.
Actually, our team, I am from mechanical, he's from computer science, and the other team both are from CS, so no chemistry students.
Oh, okay. Yeah, this time also you have that. Oh.
So 3
nice.
computer science students and he's from mechanical.
Mechanical. But all of you are interested in chemistry.
Yeah.
What about the ICERs? Non-chemistry majors, or all of you are chemistry majors participating in this competition?
Yeah, like for us as a Kolkata, the case is like we have to study all the 5 subjects. For our first year, and from second year we are to choose 3 pre-majors out of those 5, and from the third year onwards we are to go with our majors.
Okay, so you guys are still in first year.
Actually, our first year, semester just got over, and we are currently can assume that our second year, course has not started yet, but we are in the midst of first and second. So technically, we are second year.
ICER Pune?
I'm a physics major. I will be a physics major. I'll be choosing courses in the third year, like this year.
Okay.
I am going to choose the chemistry major.
Okay, so physics and chemistry. And we have some students of +2 as well. Which team I forgot? Pravar and Dev probably.
Yes.
So you guys are from class 12, right?
Yes.
Okay, great.
Which school are you guys from?
From Pragati Public School. Yeah, it's in Delhi. Dwarka.
It's in Delhi. Okay. So you guys are interested in studying chemistry in the future, or don't know yet?
For me, it's uncertain. No, I don't know yet. You
don't know yet. Okay. So you are in 11th, 12th, right? 12th. Okay. Did you guys take the KVPY exam last year?
Yeah, both classes, 11th and 12th.
And so how did you do? What was it?
Yeah, I scored 85 in 11th class and SA stream, and 10th in SX stream.
85 means you must be having pretty good rank. What's the rank?
No, I'm talking about the rank. 85 rank and 10 rank.
85 rank. Excellent. Outstanding. Yeah.
And in 12th, 10 rank.
Oh, 12th, 10 rank. Wow, even better. Excellent. Yeah. So you don't know whether you would want to study science or engineering or medical or something? You have any idea? Or still time to decide?
Engineering, most probably.
Engineering. Okay. All right. So your teammate Provas is your classmate also? Same school?
Yeah, he was in 11th class. Left in. We were still friends.
Okay. So now he's in a different school.
Yeah.
Okay.
Yeah.
So two of your your schoolmates also qualified for BioBlitz, right? So we're having a biology event as well, which is same on the same lines, but a competition for biology enthusiasts.
What's it called?
So we have named it. So it has been launched this year itself. It was not there last year. So that is
BioBlitz. Okay.
So BioBlitz also has 3 students from Pragati Public School, and 2 of them I recently saw have secured the bronze or the silver medal in the International Biology Olympiad as well.
Oh, awesome. Yeah, I like this name, Chemenigma. I don't know whoever came up with it, because it's a good name. Started last year, right? Only, Shukriya?
Yes, sir, we started it last year. So this is the 2nd year of Chemenigma. And last year we had that lab thing as well. So we couldn't do it this year.
Right, yeah. Hopefully next year again.
Yeah, hopefully we'll be able to do it next year. I mean, it's much more fun than this.
Oh, absolutely, yeah.
It's, of course, even much more hectic, but still it's much more fun.
Yeah. I mean, you spend the same amount of time probably, or maybe a little bit more in the event, but instead of sitting in front of the computer, it is fun. Yeah.
Yeah, so there we had almost how many? I don't know, from 7:30 in the morning or 8, we started the lab sessions, and it went up to probably 6 p.m. or 7 p.m.
Yeah, and also they actually did the experiments, right? That time.
Yeah.
Yeah, now I remember actually. Last year, I think you guys came for asking for reagents and other things, right?
Yeah, we were initially asking for beta mercaptoethanol.
Yeah. And then I think some reagents that, now I remember.
Yeah, and like we are also asking for the lab permissions and stuff. And then we also got one bottle from your lab for discarding some wastes.
Yeah, that's fine. Yeah. Semester is starting on Monday, I guess, right? Yeah.
Yes, sir, for us on Monday.
Monday.
For our juniors, probably 4th.
Anyway, I think the different classes starting on different times, I guess.
No, I think we are starting well. I think we have a class schedule for Monday.
For Monday, okay.
Yeah, I mean, first few days for us it is like little light because many courses will have timing issues and stuff, introductory meetings and.
Yeah, that wasn't scheduling the classes is a nightmare. And actually, I think at this point, when it comes to the department level courses, nobody wants to change. It's very difficult actually because there is very little scope of changing because many of the classes are happening for so many years. And I mean, if you go and tell them, and it is difficult actually because most of the 3 credit courses goes on 1.5 hour classes per class and 2 classes per week. And there are only 2 days we can have this 1.5 hour classes, that is Tuesdays and Thursdays. So, and if you see the department level, I think at least in OC, if you check, Tuesdays and Thursdays are fully packed. I think starting from 8:30 or something, that it goes on until 5 o'clock. I think there is no scope of changing any of these classes anywhere.
Yeah, but like for us with minors or some courses that we want to take in the other departments, they clash with the course. And now, like previously, in fourth semester, it was just 9 of us, the chemistry majors. Now there'll be integrated PhDs as well.
Right. Yeah. Yeah.
So again,
But I
scheduling
think
will be even.
yeah, actually, that is one of the reasons you were asking me whether you can take the department level courses in the fifth semester. One of the reasons for not allowing is this time clash, but that's of course a minor reason. Major reason was that some of these courses are a little advanced, and the prerequisites are there before. So unless those courses are completed, you won't get the complete grasp of what is being taught in those advanced level courses.
So participants, we wanted to know your feedback on the questions, the level of the questions or the kind of questions that were asked. So we usually circulate a feedback form. I don't know how, I mean, physically before in these cases, just have a Dropbox. So your feedback, did you like the question? Were they too difficult, too easy? You can share your opinions, anything. Whether you'd like any changes in the pattern, so that we can think about it next year.
So I wanted to say that the questions were really nice, especially the lithium, the battery bomb one. I liked it very much, the concept of that question, and also the baby warmer question that was given. And those questions were very, I mean, innovative and not the kind of questions that is being asked in the exams. So these were really nice questions, and some questions were tough a bit, and the others were really nice. Overall, the questions were great.
Okay, thanks. So for those two questions, we are all thankful to Professor Nagafani. So others, your opinions on the questions? Or even if you want to ask something to the judges, it's fine. Some general stuff. Also, we'll be releasing the results in another 5 minutes, maybe. So it's almost calculated. The scores, they are being tabulated. So just give us 5 more minutes, 5-6 more minutes, we'll be done. And in the meantime, if you guys want to ask anything to us, to any of the judges, feel free to go ahead. In the real scenario, we have the participants interacting with the judges, but sadly, it's not possible in an online setting in real life. So we can try to make best use of whatever we can do at the moment. If you have any suggestions, want to ask something,
I think I must apologize to everyone because I kept interrupting you while you were presenting. But I know it is very annoying when it is done to me. I feel very annoyed, but it is what it is. We have to do. We had to do that. We really could not exceed time. So I'm sorry for that.
Also, it seems like we have ended on a pretty nice time schedule. So we've ended almost in time, maybe a little 15-20 minutes here and there. So thank you for your cooperation. Just give us 5 more minutes and we'll be done with the scores. So Professor Das, Professor Fani, you want to say something in general to the participants?
Sure. And I don't know. I absolutely loved kind of listening to everyone. I don't think I'm half as smart as any of you at that age. So it's kind of quite amazing to see what you guys had. But yeah, another thing that I could say is if you guys have any questions, if you're excited about research, if you want to spend time at IASC, just send an email to anyone at IASC whom you're interested in. And most of us usually encourage interns, especially undergraduate interns, to be in our labs. So so you'll have an opportunity to see IASC. Hopefully this corona situation kind of recedes and you will have that opportunity. But anytime, feel free to email not just me, but anyone at IASC, and most of us are usually very encouraging of undergraduates. If you have any specific questions, do let me know as well.
Yeah, I think all of you have done a wonderful job, and I really enjoyed this program. No matter whether you win or not win, you have done a really, really great job explaining the questions. Some of the questions, most of them were really, really hard. So we really appreciate your effort. And we encourage you to pursue your passion in science, in chemistry as well. That's all from me.
Thanks, professors, for your opinions. Guys, any questions to them? You can ask. You can feel free to unmute and tell whatever you want. Any feedback about the competition? Anything? Any questions? Anything? Or if you want to know about any of the questions, that's also probably fine. Some of us will be here who have played some role in framing one of them or more than one of them. So we'll probably be able to answer some aspects of those.
Hello, am I audible?
Yes, Shantam.
Yeah. So, I mean, regarding the feedback, I mean, what I will speak, it will be less for what the quality was. I mean, starting from the prelims till the finals, we had experienced a lot of questions. So, I mean, the diversity of domains. I mean, starting from organic, inorganic, physical, organometallic stuffs and like that, catalysis, synthesis, literally everything. So, what I can say, like, we had a lot of fun participating in this event. I and my best mate, I mean, Shubhajit, we don't know how much we have done it collectively, but we enjoyed a lot participating in this event. So yeah, thank all of you.
Thanks for your feedback. So we'll try to make the competition even more interesting in the days to come. Anyone else with any feedback in that regard, you can just tell us. We'd be happy to incorporate those in the next version.
I think making questions has kind of helped a lot of us as well in clearing our concepts. Making questions is not easy. That is what we have learned after 2 years of Chemenigma and other competitions for Pravega. It is, I think everyone should practice that. It is very nice and you learn a lot in the process of making a question.
So how many of you are kind of willing to pursue a career in chemistry? More asking the participants.
For me,
I am.
yeah. For me
Yeah,
and
like I am, of course.
Yeah, okay. Yeah, for
I
me
am
and
going
Shine,
to.
both are pursuing.
Okay, so sorry. Go on.
Yeah, we are done.
And so we reach the end of this year's Chemenigma. Another year, another wonderful journey. At this juncture, I have the honor of thanking everyone who made this event possible. I take this opportunity to thank the UG Dean, Professor Balaji Jagirdar, CC, our sponsors, the judges, Professor Shantanu Mukherjee, Professor Debashish Dash, Professor Garima Jindal, and Professor Nagafani Atukuri, who are with us today, all the many participants who joined us this year, the volunteers from our batch and our junior batch who helped with making this event run. And also, I would like to thank Shukriyo for joining us in this year's journey. We hope everyone enjoyed the event as much as we did hosting it, and that everyone continues supporting us by joining us again next year.
So the results have been calculated. Anubhav will be joining our meeting soon and will be announcing the results. The tabulation and calculations have been completed.
Hello, Shukriyo.
Yeah, so Anubhav, the vote of thanks has been read out by Anvesha. So should we announce the results?
Hello, Shukriyo. I could not hear you. Can you repeat once more?
So the vote of thanks has been read out by Anvesha. So now I think we can go forward with declaration of results. Yes, I cannot hear you.
Have the certificates arrived?
So yes, I've already sent to Tejas and he's in the process of making it. Just give 1 or 2 minutes. So you want to announce it with the certificates?
You tell me. I can announce. I'm making slides, so I can do it using that also.
Cool. Yeah, that works.
Okay, please give me 2 minutes. I'm joining.
Hello everyone, sorry for the delay in declaring the results. I shall share my screen now in order to declare the results. Shukriya shall declare the results.
So we'll start with the second runner-up.
Yes, but first, just announce the name of the participants.
In the sense, okay, we'll start with the second runners-up, right? The slides are in that order.
Yes, but I would like you to first announce the name of all the finalists.
Yeah, sure. So with this, we are coming to the end of Chemenigma, and here are the much-awaited results. So we had 6 teams in the finals. Teams A, B, C, D, E, and F. Team A is comprised of Arpon and Aditya from IIT Bombay. Team B has Ankon and Ritik from IISER Pune. Team C is Pravar and Dev from Pragati Public School, Delhi. Team D has Kumar Satyam and Hardik Rajpal from IIT Bombay. Kumar Satyam couldn't participate due to some emergencies. And Team E comprises Shayantan and Shubhajit. Team F comprises Shoumidipta and Shagoto from IACS. I'd now like to have declare the results. So we'll start with the second runners-up. The second runners-up for Chemenigma 2021 is Team C with Pravar Kataria and Dev Gupta, Pragati Public School, Delhi. We'd now like to, yes, sir, you wanted to say something?
No, I was just clapping.
Okay. So we would now switch over to the first runners-up. The first runners-up for Chemenigma 2021 are Team A, Arpon Vasu and Aditya Sakrikar, IIT Bombay. And last but not the least, we'd now announce the winners of Chemenigma 2021. The winners for today is Team B, comprising Ankon Nath and Ritik Haldar from IISER Pune. With this, we come to the end of Chemenigma 2021. We would thank all the participants who have joined us on this amazing journey. I'd like to reiterate once again our gratitude to all the judges and the ISC administration for making this fest possible. Our humble regards to all our sponsors for their generosity. With this, on behalf of Team Chemenigma, I would like to declare Chemenigma 2021 closed.